going by this clock, which apparently is not actually working. So it's given a couple of minutes for people to come in, and hopefully we'll make it up during the session. My name's David Ferguson. I work at the National eScience Centre in the UK, and it's my privilege to chair this session on networks on networking. And we have three very good speakers who are going to give you an interesting time, I hope. So the first one is Bjorn Larsson, who originally is from Sweden, but is now working in Catania on astrophysics or astronomy support. Yep. Okay.
Open the station?
Yeah. Oh, I thought we had to copy up.
Yeah, there we go. Thanks for this introduction. You can hear this in the speaker as well.
Use the microphone, or do you want to?
I can use this one. Okay, thanks. Welcome to this presentation called Visualization and Data Mining in the Virtual Observatory Framework. And I'll spend some time to describe the Virtual Observatory Framework, and then I will spend the rest of this presentation to describe our software called Visivo, which is the visualization interface to the Virtual Observatory, and what we can do with that. And we use that for visualization and data mining of astrophysical data. And the Virtual Observatory is a infrastructure to maximize the use of data and to create some common tools to deal with this data. And what we want to say with this is that we want to make as much data as possible available to as many people as possible, and to develop some tools to deal with this data. And this work is coordinated by the International Virtual Observatory Alliance, and their work deals with data management, data access, and data manipulation. And their work is mainly focused on observational data coming from observatories, satellites, and telescopes monitoring the sky. And therefore, there's also the theoretical virtual observatory, which have the same problem of making as much data as possible available to as many people as possible, but they are focused on the use of simulated data instead of observational data. And our application, Visivo, is one of the tools developed to access and deal with this data. And as I mentioned, it's the visualization interface to the virtual observatory. And it's developed to support visualization and analysis of astrophysical data. And it's developed in collaboration between the Astrophysical Observatory here in Catania, where I'm working, and Gineca, which is the largest Italian academic supercomputing center sited in Bologna. And the goals for our application is to support visualization of astrophysical data with dimensions greater than 2. And with that we mean that it's not developed for 2D plotting or table view of data, but it's developed for 3D visualization of our data. And it aims at providing data analysis of the astrophysical data and to interact with databases and distributed resources to actually get some data to visualize. And it aims at being VO compliant. And during this talk, VO stands for Virtual Observatory and nothing else, as I've heard yesterday. Okay, the main features of Visivo is that it's a free, completely open source software. You can download it from our website if you would like to. And it's developed to be cross-platform, and that it runs on a Windows and a Linux machine. And it supports the HDF5 format for loading particles. It also fits for loading particles and volumes. And it loads raw data for points and volume data. And it also loads what is called VO table. And this is the standard file format for all of the applications that are developed within the virtual observatory framework and the file format which is used to communicate data between the different applications. And Visivo is also able to connect to the VCO2 web service, which is a remote resource. I will get back to that later. And it can also use external grid-enabled web service tools. I'll get back to that as well. As I mentioned, Visivo is one of the tools developed for accessing and watching astrophysical data. But there are other applications developed that are good at different things. And for data mining purposes, it's good to be able to use all of these applications together to get a greater understanding of the data. And for this, we use an application called Plastic, which is developed at the Royal Observatory in Edinburgh. And it's a messaging hub that lets all of the applications running on the desktop communicate with each other using some standardized messages. And basically one message is sent to the hub from application and is distributed to all the other connected applications. And so the application can talk to each other. And this allows us for some synchronized actions between the different applications, that we can, if data is loaded into one application, it's also loaded in all of the other applications automatically. And if some points are selected that we find particularly interesting in one of the applications, the same points are also selected in all of the other applications, so that we can follow the work in all of the applications. And this gives us the ability to interact with the same data set, but with a lot of different applications in different ways, and to get different views of this data and hopefully get a greater understanding of what we were looking at. And this is a screenshot showing an example with our application Visivo running here, and two other applications, but three completely different ways of looking at the same data loaded with a standard table to view the data and two different 2D plots and our three-dimensional plot of the same data. And as I mentioned, we are able to connect to the VCO2 web service, which is a remote resource containing a vast amount of observational data coming from different sources. And using Visivo, we can perform what is called a cone search, which is basically that we form a cone with a pointy end at Earth, and you point it out into the sky at some object, or a star or galaxy, or a coordinate. And we could think of this as a virtual telescope deluxe, because what you do when you look with a telescope is that you point it at an object in the sky that you want to look at, and it forms a cone, and you see things. But using this cone search, you can also see things that are not visible to the human eye, and we can also have a lot wider angles than what you could do with a normal telescope. And we can use this cone search to reduce the amount of data that we have to download and that we have to display on screen using our application. And the relevant points are downloaded as VO tables that we can save to disk and use later, and that we can visualize. See, and we have also deployed a web server prototype in the user interface of a grid environment using the following techniques. And it lets us use grid-enabled web services to run remote jobs that are time-consuming. And as a proof of concept, we have developed a graphical user interface for the get-my-proxy delegation, which basically just substitutes a command line operation, but this way we can keep the user within the application and using a graphical user interface instead of having to use the the command line to do the same thing. This opens up a session for the user to work within the and to access data and to submit jobs within the grid environment. And as the first thing that we can do is that we can use a hop group finding algorithm, which basically within a data set it finds groups of or clusters of points given their instantaneous density. And using our interface in Visivo, we can fill in all the initial parameters that are needed for running this job and sending it for execution. And we are given back the identifier for the job. And once we've got this far, we can save a snapshot to file containing all the parameters that we used and the job identifier. So once we have sent the job for execution, we can save the snapshot and close our application, go home, and come back later and check the status of our job and see if it's finished. Or we could keep working with other things while the job is being executed remotely. And as output, we get, once again, a VO table containing the coordinates, the density values, and the group IDs. And this is what it could look like when we get the result back with the different clusters that the algorithm found. Now I'm going to try to give you a demonstration of how the application works in reality. And this is the application when we have done nothing. We have a workspace where we will have our views. We have a control panel to the right. We can set different settings, and we have a hierarchy where all the data will be loaded, and the menu and some shortcut buttons. And first we have to actually get some data to work with, so we will load some raw point data. There are data coming from a simulation, and this data has 4 different time steps associated with it, so that we can follow the evaluation over time. You can choose any one of them, load, and there we get a object in our tree. Clicking on it, we can get some basic information about the data, how many points, how many scalars are there, and we can change some input parameters. For example, change the time step or the active scalar we want to use. This was a visualization application, so what we want to do is that we want to look at our data. So we'll open up a polydata viewer, which is the window that we use to look at points and at surfaces. Selecting it, we will see that we have the data. We can rotate the camera, zoom in, zoom out, the usual stuff. And we can see that within this data we have, zoom in, we can see that we have areas with a lot higher point density than the rest of the data. And those form some sort of clusters, and we would like to get the points that form one of these clusters. So what we will do is that we will select our points, and we will run an operation called point distribute. And all of these operations are different things that we can do with our data to transform it or derive new information. We'll distribute these points on a regularly spaced grid to get it distributes the scalar value of the points on a regularly spaced cubic grid. So you get volume data, and we can use our volume data to extract a surface from this at a given value. You can see here that we have some blobs within our data forming different clusters, and adjusting the value we will get a bigger or smaller cluster. So we choose something like this. We get the new data here, and we always get the new data as a child of the original data. And that way we can always follow the work that we've been doing, and we can always get back to the original data, so it's never lost or destroyed. We can have a look at the points and surfaces together, and it's a bit difficult to see, so what we will do is that we will change the properties of our original data and how it's displayed on screen. So we will choose to reduce the opacity. And this way we can actually see that we have the surfaces and the points. I hope you can see this as well on the projector. And turning our surfaces on and off, we can see that they correspond very well with the areas where we have higher point density. And the final step we can do is that we choose our surface and yet another operation called extract cluster. Let us select one of these clusters, and we have to wait for a while. There we have our selected cluster, and we get some information about the number of points contained within this cluster, what scalar was used to was distributed, the total and the average value of the scalar within this cluster. And we press OK to get a new data set here. Turn that on and the surface off. And if we zoom in, you can see that now we have reduced our original data down to only the points contained within one of these clusters that we found interesting. And all of the things that we could do with the original data set, we can now do with the points that we have extracted. We have them, and that was describing some simulated data. We can also load observational data coming from the real world. We choose File, Import, and we could either choose to load this from File, or we could load this from the Vizier catalog that I described earlier. That's what we will try now. Okay, and we will use the offline demo for these purposes to be sure. And now we can perform this con search, and we will select either a target name, which is the object in the sky that we want to point our cone at, or a coordinate position. I will choose the M31, which is the Andromeda galaxy, those who are curious. And we will adjust the radius of our cone around this object, and we can choose different wavelength properties that we are interested in, and we'll choose the optical ones that we can actually see. And we have to adjust or to select a mission which tells us where the data came from and who recorded the data originally. So we will choose the Hipparcos satellite as that one, and clicking on Get Catalog Metadata will perform a search for catalogs that contain the data that we are interested in. So then we can choose one of these catalogs. In this case, there were 5 matching catalogs that contain the data we want to have. So we select this one, and when we press Get Data, that's when we actually have to download anything from the remote resource. We download the data. Right. And now we have to decide what fields in the this table that we have downloaded we want to assign to the different coordinate axes for visualization on the screen. So we'll choose the following, and we have to choose what fields in the table we want to load as scalar values. I have no problems with memory here, so I choose them all. And if this had been the online version, we could have also saved the data to a file for later use. Press OK. We get the new data here. Open up a new view. and we can select our points to visualize, but they are hardly visible on my screen and probably not to you. So what we will do is that we will, instead of representing these points as simply pixels, we will represent them as spheres on the screen, and now they're visible. Zoom in a bit. And this way we have 3 of the original fields. 5 minutes. Oops. Okay. Then we do the speed version. So to add an extra scalar field that we can visualize, we could add a color lookup table, which assigns a color value to our sphere according to their scalar value. And we can choose what scalar value we want to use to assign the color. And now when we are representing them as spheres, we could also adjust the shape or the size of each sphere according to another scalar value. So we will choose another scalar value, and we will select on. And this now resizes all of the spheres according to a scalar value associated with them. And this way we now have 5 different fields, 3 with the coordinate axis, 1 with the color, and 1 with the size of our sphere. So the last thing we could do is that we could change this into a cylinder instead of a sphere. And with that we could also adjust the height of the cylinder. So we choose yet another scalar, and the height is adjusted accordingly. And now we can also change what scalar fields are associated with different properties, the radius, the heights, and the color, of course, to find some points that we find particularly interesting. And if you find this one interesting, we could zoom in a bit on the point, use another operation called point function and a picker, and that lets us select points that we find interesting. Select. Whoops. There goes my Christmas bonus. So we will skip that, and if we had selected the points, we could have also sent them to all of the other applications connected to the Plastic Hub if we had been running them. So we could have selected some points that we found interesting, and we could have got all the information that was available in the table about these points, and we could have sent them to the other applications to be highlighted and viewed as a table view or a highlighted in other different ways. And then we go to the last thing I wanted to show, which is the interface for running our hop job. Then we could open up a saved snapshot we could have, and it loads all of the parameters, including the job ID for this job. We'll see if this works okay. See if we can check the job status. Yeah, we could. And this job is, you can see that it's cleared, so it's finished, and we could download the output data from it. And I already have downloaded the output data as a VO table. Told you. So find it here, and once again I have to assign different axes, and I have to load some scalar data. Press OK. Select our points. Open up a new view. Let's look at it. And if we use the color lookup table, there we can see that this is actually the screenshot I showed earlier using the from the result using the hop algorithm. And I guess this pretty much concludes what I had to say. Thanks for running out of time, so thank you for listening. And if you want to download the Visivo software, or if you want to get in contact with us, you can visit the website. down there.
Hi there. James Farnhill from JISC. I was looking through all that. It's all very impressive. Is it something you could see would be able to go across and run in a portal environment at all? Or would you see it actually staying on a desktop? I was just quite interested with what you'd done. I mean, could you say something like Ajax, for example, to actually get it to run online rather than having to run on a desktop environment?
I would probably think that you would have to run it on a desktop. Yeah, because the graphics, I think, is pretty demanding.
Yep.
And also the amount of data.
Thank you. My name is Omar Karam from the Egyptian Universities Network. What other data mining do you do other than clustering? What can you do with the data or with the your software?
At this point, the data mining facilities are pretty limited. We have been getting the visualization parts running and using the grid environment now. We have, just as a proof of concept, shown that we can find clustering, and we'll be working on data reduction and things like that in the future. But right now, it's pretty limited.
Okay, thank you.
I'm Dan Munster from UNIC in Denmark. I'm running a Mac, but if I do download your program anyway and run it on Linux or Windows, what can I do with it? I mean, will I have access to all those libraries of data that you showed us, or do I need to get data myself somewhere?
You will have access to everything except running jobs on the grid.
Okay, so I can't use the grid facilities, but
unless
otherwise
you get a certificate to the credentials to run it yourself, then you can actually use that as well. All of the other services you can use.
And I know, of course, this is a tool that's made for researchers, but do you think, would it be possible to use it in education on a lower level than, say, graduate students at universities?
Well, I was thinking of that. I was expecting the question. It's designed for researchers, definitely. So I think for now you have to know something about astrophysics. For example, when you perform the cone search, the name M31 really doesn't...
You have to know it's the Andromeda galaxy.
Exactly,
yeah.
and it really doesn't tell you that much. So for now, it was designed for researchers. And
But with the right teacher, you could actually show some things.
Well, of course, if the right teacher would help the students through, if the teacher would run the program, sure.
Okay.
Okay, we'll move on to the next speaker, I think. That's right. Slightly better then. So, thanks, Bjorn. Danilo Ritano is giving us a presentation of volcanology. So you're okay standing right here, it's easier for the streaming. If you stick here, it's easier for the streaming.
Yeah. No. Maybe it's better. Okay, good morning. My name is Danilo Retano. I'm an electronic engineer. I'm a technologist inside the INGV, the National Institute of Geophysical and Volcanology in the Catania section. We talk about use of the broadband networks for real-time volcanic monitoring techniques. I will start my presentation with a question: why the NGV is present in Italy and in special mode in Sicily and also in southern Sicily? The answer is I will show you very few details. I don't want to talk about tectonic theory, but just to show you, the whole Italy is there is a big conflict between two different plaques, the European one and the African, that collides one each other, and they give inside Italy hotspot in many parts of Italy, especially in the northeast with the Friuli Venezia Giulia region, in the central part Apennine ones, and with Campania, Lazio, and also in southern Italy, Calabria, and first of all in Sicily. In particular, so INGV has made a map that represents risk, and as you can see, the part I show you, northern east, central part, and also southern part of Italy will be interested by high risk assessment, and also they represent seismological dynamic points. As you can see, a zoom will show you better than for Sicily, will interest us very much. So what about the part of Sicily? Sicily, as you know, is a well-known high-risk region because volcanic eruption and also seismic activity produce a wide range of risk, also for inhabited areas. And the presence of strong earthquakes and explosive volcanic activities could have deep impact on the local population and also generate considerable damage. So, let's come again to the zoom. Not all Sicily is high risk. As you can see, the eastern part, with the presence of, for example, the Strait of Messina, southern Calabria, the presence of Aeolian Island, Mount Etna, near Catania, and also southern part of Sicily, with the deep fault that we call the Scarpate Bleomaltese in Italian, are very dangerous and important part to study. The presence of Mount Etna, the highest active volcano in Europe, and also recent activity of Mount Stromboli, starting from 2001 till 2003. They represent natural systems that are suited to be studied, and we use all present technologies. So our institute is inside the territory, and our centralized national seismic network recover and records every year thousands of earthquakes. Most of them are instrumental, but part of them are with magnitude 3, starting from 3 to more. So also volcanic studies shows that municipalities and also countryside around Mount Etna are very it's important to point out the impact that lava flow could have on the countryside around Mount Etna, especially in the past and also nowadays. So the Istituto Nazionale di Geofisica and Vulcanologia, especially the section of Catania, is the sum of different institutes, and it was founded in September 1999 and become one of the largest European research institutions. He is involved in the field of geophysics, seismology, and volcanology. And to be able to control the whole territory, we are present with 8 main departments around Italy: Rome, Naples, Milan, Catania, Palermo, in Sicily. Also Pisa. And in particular, the section of Catania studies all active volcanoes located in the eastern part of Sicily, as I show, and all the regional seismic area. So, in 2002, inside the INGV Catania section, started a new group, Research and Development Division, that is called the Unità Funzionale Sala Operativa. This group is involved in activity that regards monitoring and surveillance, and not only during regular activity, so normal times, but also in presence of seismic crisis, volcanic eruption, and so on. So in order to provide a stable control and surveillance of this area, the UFSO staff develop and plan new monitoring techniques that are based on real-time processing. So they help us to understand the volcanic activity and to evaluate correctly high risk and hazard. So UFSO has inside the center of Catania a monitoring center that we call control room, and it is located in the main site of Catania. In this center, all data coming from remote stations and all remote sensors are collected and are available in near real time. So the monitoring center is operative 24 hours a day for 7 days a week, and of course for the whole year. And UFO staff is involved in data acquisition, storage of data, visualization, and also web publishing in real time of the most important parameters. Just to give information not only to researchers but also to common people. So inside the monitoring center, there is an automatic, semi-automatic system. All signals coming from different kind of station are first of all acquired, then analyzed, and then visualized in the control room in near real time. Near real time because we use different kind of transmission system, and we use satellite also. So the delay of satellite we give us the opportunity to have robust data, but real time, not only near real time, with few delay, few seconds. So we provide accuracy of this data and robustness. And all the obtained output are, as I showed you before, immediately available. And they are continuously compared with some threshold. In case of emergency, we are able to send immediately alert message with faxes, with SMS, with mail, to civil defense, to municipality, and also to on-duty personnel that are inside our staff. So, what about monitoring and surveillance? How is possible to record the breath of a volcano? The principal key is if you want to have a picture and a complete state of health of a volcanic area or a seismic one, and if you want to be able to record in near real time every minimum pattern variation of, for example, the volcanic activity, we have to set up different network around a volcanic area or in the important locations, and to acquire different kind of patterns. So we have around Sicily our monitoring networks that continuously record data. As you can see, we have some sensor, multidisciplinary sensor located in each station, in the island of Stromboli, in the Aeolian island Vulcano, and also the island of Lipari, in the Straits of Messina, and also southern Calabria, to reduce a parameter that is called gap in seismology. And also, you can notice the great amount of stations around Mount Etna, and also in the southern part of Sicily. For example, seismic network is composed by analog and also digital station. We have short period broadband and very broadband sensors to have different kind of frequency acquired, and we use both radio and satellite transmission. This is an important thing because try to imagine what happens during an earthquake. Wired link, radio transmission could fall, and we have loss of data. Instead, satellite, even if they give us near real-time operation, guarantee robust systems. And in case of damage, we repair only the dish, but not the satellite. This is another example in the island of Stromboli. After the eruption of 2001, in 2003, the island was completely covered by sensors. And other kind of sensors are GPS measurement that are able to measure distances between two different points. And they give us information about ground deformation, tilt meters, and also magnetic measurement. We use from 1985 also video cameras, first in visible, but then in infrared and thermal images. So lots of cameras are put in a particular location, the island of Stromboli and also the Vulcano, but we cover also Mount Etna, and we receive an image, streaming image from Mount Etna, the summit crater of Stromboli, and also the island of Vulcano. Here is an example of monitoring, real-time monitoring of Strombolian explosion and lava fountain activity of Mount Stromboli. As you can see, it's possible to have not only the visible image, but also the different temperatures of lava fountain. And one other example is gas measurement. We measure the plume of summit craters and also some ratio of gases like SO2, ACl, HF with a technique that is called FTIR. So inside the EFSO, software development is one of the fundamental areas, and we try to develop hardware and software architectures. So they give us the opportunity to analyze and visualize online data. So the use of hardware and software for real-time systems requires a very large number of broadcast connections. In particular, the INGV Catania section has different sites because we prefer to collect all data inside in remote station, and if there is the loss of transmission system, we recover the data when transmission is up again. So starting from INGV Catania section, the main site, we have a data acquisition center in Catania. This is sort of a great repeater that collects all the data. And also we have Stromboli and Lipari, two different acquisition centers. Around Mount Etna we have Nicolosi and also Milo site. All of them are GAR connected, and also there is a backup lines, some backup lines with wireless LAN. In particular, for seismic transmission data flow, we use an open source file that is called Earthworm, and we have located some local buffer that are able to collect data from remote site and then transmit to our center in Kuwait. We have developed dedicated software, in particular one software to generate virtual drum recorders, and we use only the Earthworm system to perform acquisition, and all of the stations are wired connected. About video systems, we have realized to guarantee streaming, single frame and time-lapse, customized software. So we have three different kind of images: real-time video streaming, single frame acquisition, and also time-lapse digital video. For the last one, we have realized the customized software that is able to realize film 25 frames per second, but with a particular feature that is near to time-lapse. We need to visit and see a particular acquisition of Mount Etna, for example. So every single frame acquired once every 2 seconds are connected in one time-lapse film. So we obtain 15 minutes of data acquisition. They are compressed in only 18 seconds. This gives us a great advantage, especially for expert-on personnel trying to imagine the volcanologist, because they are able to evaluate volcanic activity, observing 24 hours a day, image in very short time. So during last years, monitoring active volcanoes has greatly augmented, and we use online multidisciplinary analysis on some physical and geodynamical parameters. But of course, we have great amount of data, and for this reason, we do massive use of broadband connection. So what we try to do now is we are able, for collecting all this data, to develop new dynamic and adaptive models that are able to show us the behavior of volcanic and seismic area. Some example. There is a correlation between a particular seismic signal that is called volcanic tremor with lava fountain activity. In this picture, it's possible to see different steps of a lava fountain shown by our cameras, and these signals grows and at some different point. The important thing to do is at point 1 to point 2 establish an alert system that we use to alert municipalities and also civil defense. When we are here and we see the volcanic tremors is improving, we send fax to municipalities and also civil defense. But this system is able to prevent, in a sort of way, ash fallout. Because don't forget that when there is a lava fountain episode, it is possible to have ash. And sometimes we call the airport, for example, the airport of Catania. They decide to stop the activity or to modify the airplane routes. One another automatic system is able to do the pattern recognition of stromboli explosions. System is called VAMOS, and through the line analysis of infrared image, it characterizes and clusterizes all the explosions. So thank you, that's all.
Do we have some questions for Mariola?
Hi. The thermal imaging cameras, are you able to capture data from them online just as a web camera?
Yeah. We have different cameras in different location. We monitor Mount Stromboli, for example, Mount Volcano, and also Mount Etna. We receive them in our site, and then with streaming and single frame. So we publish all the data in real time also on our net.
Okay, thank you.
No other questions? Oh well, we'll try and wrap up a couple of minutes and go into.
Okay.
Thank you.
Thank you.
So now we have Cesare Mazurek, who's going to talk to us about digital libraries.
Yes, thank you. Hello, everybody. After those two tremendous presentations we saw, I would like to point your attention to digital publications and digital libraries, which we have developed in a pioneer network, which we have been developing in a pioneer network for several years, and which became the kind of critical mass for metadata harvesting in our network. And those results of those metadata harvesting might be the basement of high-level content-based services, higher level content-based services provided as the network service for further applications. So the project is based on a pioneer program which is in Poland, which has been developed for the last 5 years. And the network construction is the one part of this program, but also there's a set of applications, services, technologies developed in the parallel programs, projects, which constituted that program, and which were also in a one part devoted to content enrichment in our network, the content-based services enrichment in the National Research and Educational Network. So we have the Pioneer network based on optical fiber infrastructure connected to JAN network, and we are working on a content-based services in this network in particular teams. So last year, Terena conference, as maybe some of you may know, had place in Poznań, and during my presentation I had this slide presented with the digital library installations in Pioneer. It was the year 2005 when we had 3 installations, and up to end of 2005, what is written in my paper, we had 5 digital library installations in Pioneer. We had some in configuration phase and some which are here on the yellow in the test phase. Currently in 2006 we have already 9 installations which are working. Those digital libraries are mainly in the scientific environments, in the institutions like universities, but some of them are typical regional digital libraries, so they bring together librarians and university librarians and public librarians to enrich the content, which is mostly in 3 areas of content. One is the educational one, when we have the scripts, academic scripts, and publishing editions of academic books. The second area is the cultural heritage, when we have the resources which are usually not available for plenty users, which might be only accessed by very high level scientists, and which are completely unavailable for people who are outside Poznań or Toruń or other larger cities. And the third collections, usually third type of materials, are the special materials from region, like newspapers from 19th century and many others. So we had some assumptions building the regional digital libraries, and those digital libraries had to at first support multiple content types. So we assume that some librarians want to put just images, some advanced people want to prepare HTML code and prepare nice websites, web pages devoted to present particular publication. Some of them have only PDF files and they want to upload PDF and provide it to users. So the framework which had to cover this functionality had at first to support these content types. Another assumption was that we have to build the hierarchy collections of these publications, but these collections shouldn't be hard-coded for digital library. That means that some new collections should be possible to create by not by administrator of digital library, but also for users and for editors of digital library content. So there's a hierarchy of collections. I will show you in a minute the example. The approach of building digital library came to us from the idea of building the electronic publishing system, And we were able to provide the resource versioning mechanism, which is very important for digital libraries when you have to provide the resource in a continuous way. You cannot move this from one page to another or from one address URL to another. Even if a new version of document appears in the digital library, it must be with the same identifier or with the same URL accessible for many years. So the resource versioning. Advanced support for resource metadata. So that was the main assumption, that we are not building the collections of publications, but we want librarians and educators to extensively describe these publications with the metadata. We assumed the Dublin core metadata scheme, but also we provided the librarians and editors the opportunity to add their own attributes, their own schemas, to define new schemas, what they want. So also for historical reasons, we had to assure that there will be MARC support and some exporting functionality for RDF descriptions. Okay, next assumption is about the searching, and it is mainly for users of digital libraries. So we came from in this point, we came from the assumption for editors, which are mainly librarians, to assumption for users. Searching mechanism, which should be not only local in the digital library of particular region, but also searching mechanism on the level of national platform of digital libraries, and also support for indexing by Google and other searching engines to find the publications of digital libraries in our regions through those engines. Extended access management, it's another assumption for users. Some universities have authentication based on LDAP, authentication based on LDAP protocol. Some wanted to use the single sign-on mechanisms. So we had to provide a flexible environment for usage of external authorization mechanism. We had also RSS-based notification for digital libraries. That means that the content comes to users, not users are looking for it. So with this assumption, we built in Pioneer Network for last three years kind of multi-tier distributed and portable digital library platform. Here you have some examples of operational digital libraries, and you can see here is the digital library which works in Toruń region, which is called Kujawsko-Pomorska Digital Library. And you can see, for instance, that there are collections here which they have in their digital library, and the collections are multi-tiered. That's the main collection of digital library. We have cultural heritage here. We have the regional materials here. When there are two sub-collections, one is of particular region near Toruń, and one is about materials coming from Lithuania, or about Lithuania. Another example, which was the first actually, is the Digital Library of Wielkopolska region. And we have here just simple mechanism of 4 collections, but here are, for instance, the recently added publications which are automatically presented to users. The Digital Library of Zielona Góra is an example of library with an extensive metadata descriptions. They have lots of postcards from the Second World War and early 20th century, described with a large set of metadata. And what is also visible here is that the particular postcard, which is stored also in a kind of miniature of image, is assigned to group publications. So if I found in the internet, if I find in the internet one postcard, I can, through the metadata description, come to a whole group of postcards which are stored in the digital libraries in a particular topic. Okay. I mentioned that there are support for different content types in the digital libraries in Pioneer Network, but the most used format is Deja Vu, which is a very nice format for picture presentation, like images or old photographies or even scans of old books. And here you see the plugin of Deja Vu from Lizard Tech, and there's a nice functionality to get some part enlarged, or to browse or to zoom the particular parts of picture. The basement for the whole platform is the proprietary software we have developed in PSNC since 1999, and I had some presentations on Terrana Networking Conference, so I will not go through this. You can follow the link here and find all the regional digital libraries installed in Pioneer, and you can find information about the digital library framework, the Libra. Maybe the most important thing is that this is a Java-based application which is allowed to be installed by editors with web installation tools, and we can easy update the software and configure it for users with the GNLP protocol. So the main basement for the metadata harvesting in such kind of distributed digital library environment was the architecture of digital library. And we had, as I mentioned, we started the Libra development in 1999, so we had to build a service-based we had to apply the service-based approach for this infrastructure. So we found out what are the main functional group of digital library software, and we added one service for each functional group of digital library, coming with the service-oriented architecture for this platform. So you see readers which are users of internet, and they access digital libraries through web server, which is communicated with internal low-level services provided in a form of independent services which might be installed on several systems distributed in the network. You see the editors which have which have the end-user application written in Java, and one administrator per installation of digital library. Those servers might be installed in different parts of the network, and they providing the one virtual or one distributed instance of digital libraries like I've presented before. So with this service-oriented architecture, as you know, each service can be deployed on different hosts. We can, for instance, index resources on one server and store metadata on another. Services does not need to know their locations. They might be managed dynamically. Services can send and receive events, so they communicate through events, asynchronous events. The implementation is easy to be replaced, so we can use some modules which are added by external authorities or local situation like LDAP authorization or others. Also, services can access each other with the service authorization service authorization system, and there are external services which might be accessed if authorized, of course, like through interfaces like Java RMI and Open Archive Initiative protocol metadata harvesting. And this last thing is what I'm talking in our paper here. Actually, we have the service layers. We have the services split it into two layers. One is the service layer. One we can say it's a user interface layer, and The main functional services are those 5 services with the supporting of 2 type of services. With the functional services, I can start with the metadata service. And the metadata service is used for everything which digital library administrator or user or editor wants to do with metadata. It means that editors can add the metadata to the system, the administrator can build a new schema, and the metadata are also used for storage of construction of collections in the digital library. So that's the information about what are the collections in the digital library. The content service is everything which contains, is regarding to the content, so storage files, some transformations, some backup of the content for particular libraries, for instance. The search service is one of the largest services in digital library, the Libra, and this service is searching through metadata as well as through full text documents. It can extract the text from documents like PDF, Deja Vu, HTML, OpenOffice or others, and index those text documents, as well as indexing metadata in this in particular installation. Also, as we have several installations of digital library, we took an approach for gathering metadata from all digital libraries in every digital library installations, so we can browse and search a whole platform. User can access the resources from Toruń Digital Library by searching in Wielkopolska Digital Library, for instance. And for this functionality, the support is provided by distributed search service. This service is storing the information which is used to find out when we should look for metadata in other digital libraries and what are particular collections they have. User service is everything which is involved in the user management, group management, rights management, and so on. So this is main functionality of services, and we have also supporting services, which is the base system service like service broker, service address localization, and so on, and also event service for notification support of notification between services. So that was the server installation and service layer for digital library. We have another layer which is user interface layer here, and there are 3 types of user interfaces to digital libraries in Pioneer. First is the web interface for users. We have the implementation of servlets, which is used in standalone installations when we build a new digital libraries system. But also the services might be accessed from the portlets, and this is, for instance, the approach for more advanced services when we want to join digital library with Grid or with telemedical system. Then we use the portlet framework like GridSphere or others to provide the access to digital library from external services. Another interface is this editor administration application, which is Java-based application I mentioned about. And the service monitoring and management interface is based on Java management extension, and it might be used for external applications monitoring the digital library behavior, the load of events, the state of publications, as well as it might be used by SNMP, through SNMP by other network monitoring applications. The last release, 2.2 of the Libra, was announced in early March this year, and we had provided several new features, like you see here, but the most advanced or more aggressive one was this distributed search through several installations of digital libraries in a Pioneer network. And to use this or to realize this, we took the approach provided by Open Archive Initiative. A protocol for metadata harvesting was the basement. And the story about this protocol is started in 1999 in Santa Fe, when the group of people started to work on the selective metadata harvesting, and they addressed all those questions around this issue in Santa Fe. In the document they worked out in the Santa Fe, that was the 1999. And then they worked out all the criteria for selective metadata searching through different repositories. They started with the basic terms. So in this protocol we have several objects. First is this, it's called harvester, and this is the system which wants to provide the content, which wants to access metadata stored in a remote system. So it's a client, and the repository which provides the content and wants to allows to access its metadata by external systems. The element is the basic object, like publication, described in a repository, identified by identifier, which should be unique, at least on the level of a particular repository. We have records, which are elements, the metadata in particular format, so that's the quite flexible approach, but the must is the DC format, Dublin Core format, to be supported. And the set is the last term. It's the way of grouping elements in a repository. So it's kind of collection from our approach, but it's a way of grouping those elements in sets which might be created in a hierarchical structure as well. And each set can have subsets, and each element can belong to any number of sets. Also for none. Other features of PMH, Protocol for Metadata Harvesting, is those important criteria for selective harvesting. And this selective harvesting is based mainly on two features. One is the last date of resource metadata record modification, and we have here two situations. One when we have the modification of particular attribute value, and the second when we have the modification of metadata schema. And the second criteria is the element of element membership in a set. So through the request over PMH, we can ask about the membership of a particular set of a particular element. Other features are also supported, are also suggested in this protocol, is for keeping information about the deleted records, and also a very nice feature of which is called list of friends. For particular repository, we can define the friends repository, which are very easy accessible and discoverable in the network, just through putting them on the list of friends of my repository, for instance. And communication in the PMH is going through a set of requests. First, or the simplest request is the identifier request, which gets the information about the repository and its friends. The list metadata formats is the request which gets the information about the metadata itself, about the formats, it supports, and as I mentioned, at least Dublin Core must be supported. List sets provides the list of sets which is available in the repository. Get record gets a single record based on identifier. List of identifiers gets the list of identifiers of elements available in the repository. And list records gets a list of metadata records available in the repository. So basing on this protocol, we started to extend services in the Delibra, in the digital library environment, to provide the metadata exchange between all those installations, and to allow or to ensure the periodic metadata synchronization between those installations. So we use this selective harvesting based on the data of modification of particular resource, and we also keeping the information about the deleted records. Our collections from digital libraries are transformed to sets. Our metadata are transformed to the Dublin Core metadata element description. And what we had to ensure, because we have 5 or 9 or currently 9 or more digital libraries which we want to access by one interface, we had to extend this protocol requirements to ensure the unique identifier of resources. So these identifiers are unique for whole platform. We use the OII identifiers. And each digital library in this approach has all metadata from whole platform. So what about the implementation? Delibra, as you saw at the beginning, have the service-oriented architecture, so we had to split this protocol metadata harvesting support for different services in the way that Delibra would become the repository for PMH as well as harvester when it gathered information from other digital libraries. So we implemented this in a version compatible with the OII PMH 2.0 from last year. And we use two services from Delibra. The repository interface is embedded in the web service. It's in the web service. It's because the communication protocol for OII PMH is the HTTP, so every request is coming through HTTP. And through this user interface layer web service, we provided information about the deleted elements, about the sets which are in the digital library, about the flow control, what elements are moved from which set to which, and globally unique IDs. This is the repository interface, and the harvester was implemented in a new service which is called distributed search service, and this service stores the list of repositories which are harvested, and it's starting a periodical harvesting which is configurable by the digital library administrator. What means that, for instance, now we have one process a day for harvesting whole metadata systems, and it's during during the night. But sorry. But when we move this indexing feature to external system, it will be more often to get those data. So this implementation and this protocol which is operating now was used to start thinking and building prototypes of content-based services. And we provided two group already from this group, we provided two services, the distributed searching and virtual collections. Those services are using the metadata description and itself the protocol for metadata harvesting to extract some information, more information from metadata, and to provide a new view of digital library platform in a Pioneer network. So distributed searching is an easy to understand. Users which comes to one web portal wants to get the metadata harvesting results from different installations. So just transparently, but they have to click on the button. They get the search results, both local or remote, from local or remote resources, which metadata match the user query. Another thing is that this service might be also accessed not only from web server or from users to web server, but also by any other network service or information portal. So we can provide for educational portal or for schools portal, for instance, new publications which appeared in the collection of books for first or second level school, for instance. And this is very poor visible here, but a bit here. When the results, when I ask for, for instance, for a publication which in a description stores the name of the city Toruń, I get the more than 50 publications, and those which were locally provided by Wielkopolska Digital Library are, for instance, here with the factor of heat, and here with the OAI questions are answers provided by other digital libraries. So that was the first. And the second, the virtual collections is more advanced, I would say. You know that we have the static collections in digital libraries when the editors can assign the particular publication to one or more collection. And that's all. I mean, when I'm looking through the collections, I can get the information and impression what is the publication in this particular collection. But also there's a lot of information in metadata. So we provided the service to build the dynamic collections, which are based on a set of conditions that object metadata must satisfy to belong to the virtual collection. And this service is based on RSS feeds. It's provided to users based on RSS feeds. So it means that user define, for instance, I want to know every publication. I want to know about every new publication which appears and which is written by a particular author. And then the virtual collection is built for him, and he's provided with this information in the feed of RSS. And this is the first level of unification of publications, but also virtual unification, but also we can approach unified collections, which is approach for grouping some collections from different digital library instances, just bringing them together into one virtual collection. But this is the more complicated thing. We are working on this now, and this is the first of all we have to decide if we will unify the names of collections or if we will use the advanced metadata exploration tools. This is the example of a virtual collection with the RSS feed. We were asking about the chemistry materials coming from different digital libraries in Pioneer, and we have all the publications here in this feed. So in conclusion, some numbers. We have the 9 digital libraries in Pioneer based on the proprietary Delibras software. Those digital libraries have already over 2,500 publications, which are digitalized, available, and searchable. 70,000 of attribute values in dictionaries. There's a set of dictionaries and thesaurus services for attributes. And more than 300,000 reference to these dictionaries means that every publication is roughly described with 12 or 13 attributes. So it means that we have quite lots of metadata to explore and to provide new services based on this. Okay, that's all. Thank you very much for your attention and some questions.
Do we have any questions for Cesare? Everyone's too keen to have their lunch. No questions? Okay, well, I'll thank all 3 of the speakers who've given us very good talks, given us some view of the high demand activities that have to be supported by the network. So thanks to all 3 of the speakers.
it's lunchtime.
Thanks for the talk. It's good. Thanks. Be in touch.
You got my email?
Yeah. Yeah. Thanks.
you need to demo something, or no? You're on that. Yep. It's all loaded up. Take a quick look. Yep. Just I'm just doing the startup slides right now, so we just. This is actually Martin's machine. She is doing the demo.
Right.
Yeah, oh yeah. So you can't get in.
Fantastic. That looks
No, I downloaded these both.
great. Thank you.
Changing the music.
That one makes sure it's sensible. Perfect. Okay, are you happy enough with what you see there?
Yeah, yeah. I said there's a lot in there. Time if you want to do.
Yeah.
Some questions.
I understand.
Yeah.
I have actually, I'm going to gather this particular one, but I borrowed 2 slides as already from 1 minute.
Okay.
So I'm normally happy enough.
You're good.
Would you be keeping an eye on time, or should I?
Well, I think I'm time for one. But you know, I mean, we really want to shoot for is spin as well. I think it's after lunch break we'll probably start moving on. But so, but I don't want, we won't cheat on it. But sort of total like 20 minutes. So we have some time for that.
Could I ask for a warning after 15, because I know where I should be after 15, and then should finish the rest of it at 10.
Yeah.
Okay, where would you like me?
You don't sit up here. You guys sit in the audience. So
I see.
Yeah. There's a hand mic also. Whichever one you use. Just be careful about doing too much pacing because you're at the internet cast. So you can use the hand mic. You should be on. So we'll give a couple minutes if people still come in from lunch. So good afternoon. I'm Ted Hans from the University of Michigan, the chair of this session and the following session in this room. Just want to make sure you see the slides up here. There's information in here that's important about the meeting, and particularly, it was just pointed out, make sure you bring your badges tonight to the gala reception because your badge is your identification, your ticket into the gala reception. So please do that. And also, as it says right now, don't forget to also fill out the evaluation forms online and report your feedback on these meetings. We'll get started with this session. We have 3 interesting presentations in this session, touching on areas of network management and measurement. Our first speaker is Dave Wilson from HEANet, and I'll invite Dave to come up, and we'll start his presentation. And Dave will have time for answering a couple of questions at the end of his talk, and we'll do that for each speaker through this session. Dave?
Thank you very much. Thank you very much. Is that working now? Thank you. As Ted said, I'm Dave Wilson. I work for the Irish National Research Network, and I'm going to be speaking about something which, if any of you were at TFNGN a few months ago in Cambridge, I brought it up then last thing on Friday evening, and there's been some amount of reaction to that since then, so I'll be expanding further on that here. The topic in particular is that we have the ability now, or will have the ability very shortly, to create layer 2 circuits across Europe. And I believe that there are some implications to our routing and how we perform routing within college campuses, within NRENs to other customers, and between NRENs, which will be affected by this new service. So the way I'm going to run this down, I'm going to give a very quick introduction to the topic. I'm going to spend about 60 seconds or perhaps slightly more on JRA3, and that's the interdomain bandwidth on demand project itself. And then I'll spend slightly more than 90 seconds, I do apologize for the lies on my slides, on the raw background of campus networking that I think will be affected by this particular problem. Then I have a problem statement, and I will try to present some solutions. Now, I'm disappointed to say the solutions, none of them are perfect, but I'll try and highlight in what ways it's not perfect and what's most suitable where. So this won't be a magical new technology. I'm afraid I haven't been deep sea diving or breaking land speed records. In fact, looking at some of the faces in this room, there's probably nothing here which is technically going to be new to you. What I do want to highlight is that I think that there are, well, as I said, there's implications for IP routing here. There will be particular ways to solve this problem, and it's not clear to me who is solving the problem. So that's what I wish to highlight. The JRA3 project itself, you are currently, I believe, not right now missing the presentation, but I will not be so cruel to my chair as to suggest you all rush out and see it. But JRA3 is being discussed in another room, and I just want to mention that this isn't actually part of the JRA3 project that I'm covering here, but an implication of it, and I'm covering this on my own time, as it were. So with that disclaimer in mind, what JRA3 is doing in about 2 slides is, since national research networks everywhere are working on providing layer 2 services end-to-end from user to user, wherever those users might be, these do meet with JEON2, which is also providing exactly the same service. So it is possible to create an Ethernet VLAN from a location in UCD in Dublin through JEON to a location at another university anywhere in Europe. The JRA3 project in particular is looking at a manner to implement those services in a coordinated way, so that a single request will set up the 2 or 3 or 4 VLANs necessary to provide an end-to-end service to 2 users in 2 arbitrary locations in Europe. And they do this in a fairly technology-independent way. It's a layer of implementation where you make a single service request between 2 endpoints, and they work out what the correct services to ask for those services are. The services are requested and reported back to the user. The way this works, I'm very sorry for the small letters here, most of them aren't terribly important, but the cloud at the very top, which I will try to point to, is if you imagine a bandwidth on demand service on any given NREN, which in this manner is implemented using a grand total of 2 Ethernet over MPLS routers. You can add some more as you wish. There is a domain manager within JRA3 for that service, which handles if you like, the technology specific, or not quite technology specific, but is the most direct communicator through a technology proxy for the interdomain service into that network. So the services are requested by this, but not the user does not interact with the domain manager. There is a second device called the interdomain manager, which communicates both with the user and with the domain manager for that given NREN, and with other domains. So if a user requests a service, an end-to-end service that is implemented by 2 or 3 or 4 NRENs, the inter-domain manager will, the person domain manager that receives a request will take the job not just of setting up that service, that giggy circuit, if you like, within its own domain, but also of transiting the request on to the next appropriate NREN, or the next appropriate domain. It may more than likely be JN2 in that instance, and onward to the 3rd domain, and 4th and 5th where necessary. So, as I said, the NREN, or the user, by doing that, will be able to create arbitrary layer 2 paths between arbitrary locations. This is fantastic. The JR3 system will be able to arrange the setup of all these paths, and users will have the, in quotes, the ability to connect anywhere inside of Europe and onward if the service is further extended. So the benefits of this, okay, we had the talk yesterday over circuit switching versus packet switching. We're not going to try and actually convince anyone here. The reasoning behind it is it gets users off the IP network, it gets some the big guys onto their own circuit switch backbone. We can tune the IP network as we wish. I'm not going to sit here and give the party political broadcast, but it does give the user more control, which is a double-edged sword. And I'll get back further to that in a moment. From the other direction now, looking at the point of view of the campus network. Every campus, as far as I can see, every campus I've visited is different. It has different needs. Its users have different requirements. They have, and Andrew, I think I borrowed these criteria from a talk Andrew Cormack gave about 5 or 6 years ago at this stage, and it's run through my head since. Every single user will have a different set of needs and a different set of priorities for those needs. And so, as we saw, I think, in one of the last parallel sessions, they tend to be mutually contradictory, and it's quite a tough job for the NREN to juggle those requirements. So the system needs to be secure, the service has to provide regular production traffic and be reliable. At the same time, we have to provide for research needs, research networking needs, networking research needs, which may break the network, and that may be the only way that you can learn, as someone said earlier, is from breaking the network. We have essentially home users in campus accommodation, which is a whole can of worms for another time, I think. But the short version is these requirements are all entirely conflicting, and each IT department or each computing services department in each university or further education institute will reach its own conclusions about how to serve those users best. And then they provide this link to the internet. And this, as far as I can see, on the whole, in the past, has been a single link from the campus to the NREN, or perhaps 2 links, perhaps in extreme cases 3 links. But as far as I can see, there is a link or a small set of links that provide service from the campus to the rest of the world. And there has rarely been much more complexity about that. I know some of our customers in the past have been BGP multi-homed. There are plenty of universities out there who are. There are plenty more that aren't. And that's as far as the complexity has ever gone. So there will be some physical link there. There will be some sort of routing policy, which is more than likely specified by the NREN or negotiated between the NREN and the customer. The negotiation may take the form of the customer saying we really need to do X, Y, and Z, and the NREN provides to implement it in a certain manner. Or it may be the NREN turning around and saying we would like to configure your routers for a BGP. Here's a config to deploy, please. Either way, the way this link is implemented and the way routing is implemented is going to depend primarily on the requirements of the IT department implementing the requirements of their customers, and on the service specification of the NREN itself. So, a little bit more detail on that. I'm very sorry for those who are already fully familiar with this, but I do want to spell this out to make the later implications clear. A routing policy I will define as a list of IP prefixes that need to be routed, and information on how those prefixes should be routed, which may be some sort of preference if you wish to express a preference, or some sort of distance if you wish to express a distance, or marking one as backup and one as primary. This assumes a certain amount of hierarchy. The way the hierarchy is implemented in the European region is that a regional internet registry, so the RIPEs or the ARONs of the AP NICs, but the RIPE in this case, will give addresses to a local internet registry, which tends to be an ISP, which in our case is probably going to be an NREN. the NREN, or excuse me, the LIR provides stewardship over that address space and assigns it to the customer. And the network in particular, as it stands, is built around this very hierarchy. So our topology, to a fair extent, is inherited from the assignment of addresses here, to an extent. There's been some feedback either way, but this is how it's fallen out these days. There's a way to build networks. There is a way to connect people to the internet. And because of the way that we have developed these policies, it tends to follow this form. The hierarchy looks a bit like this. We have a bunch of universities. We have NRENs connecting those universities. The NRENs may have arbitrary connections between them. The universities tend not to. Beyond that, the hierarchy sort of breaks down above the NRENs because you can have arbitrary routing between the NRENs because they all tend to be local internet registries. They tend to have their own provider-independent address space, their own AS numbers. They've got all the ingredients, in short, for being able to route arbitrarily between themselves. So if an NREN wants to bring up a random connection to another NREN, no problem. There's ways to fix that. If you want to get that connection to do exactly what you have in mind, there may be some stupid BGP tricks you have to implement it, but it can usually be done without too much pain. It has not been the case before now. Okay, people mention ATM. But in widespread deployment, as far as I can see, it's never been the case that users created arbitrary layer 2 connections between arbitrary locations. And what I was getting at earlier on then about the bandwidth on demand service, it has the ability, if it is widely successful, to change this assumption. And in the same way, if this assumption is not changed, then it may impact the success, I guess, of an inter-domain bandwidth on demand service. I shouldn't say it will impact the success. It will be implemented one way or another. But the applications for which it can be used may be limited by a layer above, by the IP routing that can be run over it. So the problem statement, if you like, then, if I haven't spelled it out quite clearly already, is technology exists to create these LANs across Europe, but the addressing still assumes the old hierarchy, and it now seems to be the case, whereas before it was just as easy to get addresses, get the right addresses in place, get the addresses you needed in place, and get the routing in place, as it was to dig a trench in the ground and get a circuit from one location to another. It's now much, much easier to bring up random gig circuits around Europe between two locations than it is to configure the routing between them. Because configuring the routing between them is likely to involve a certain element of bureaucracy and might involve quite a lot of technology changes. What I have in mind here is, and even before we get into the implementation itself, we have had fragmented address allocation in the past. If we have arbitrary connections to arbitrary locations, then we need to have arbitrary assignment of addresses in order to fully support that the way people might have in mind. We tried this in the past. It didn't quite work. We ran out of Class B space in a rather big hurry. And so the workarounds to that have led to the setting up of the regional internet registries. So it's still possible to get fragmented space if you can justify it. And this is one reason that I'm taking care to spell this out. I know an awful lot of people have seen this already. I know it's bread and butter to many of us. But I have seen in the past people asking questions like, well, do you think your ISP will give you enough space for that? And the answer is the ISP will give you the space if it's justified under right rules. And the right rules require you to be able to justify it. They require you to be able to write down that you're doing this in a manner that will require this use of addresses over 2 years, and there is no other sensible way you could perform this project. So the addresses can be got, but the implementation of that is a different story. So the way this tends to be implemented is that ISPs, and by ISPs I include NRENs, but it's not limited to NRENs, but we are in this case providing internet service. They take stewardship of a block of address space from the regional internet registry in question, and then the connectivity for those addresses, I use PA addresses up here, provider allocated, is dependent upon the NREN. A very common question I get in my role as an IPv6 hanger-on is, how do I get IPv6 addresses? And this tends to be the first question out of the mouths of people who are looking to get some sort of IPv6 connectivity. And my answer to that is always, it's not very important. Work out how you're going to get connectivity, and the addresses will come with it. So in this case, you have a set of typically IPv4 addresses, but I'll get to v6 in a moment. That's another kind of worms again, which the connectivity for them is, in theory at least, solely dependent on connectivity through the National Research Network itself. You can probably see where this is going. And to back this up, I'm going to mention a paragraph from the current RIPE IPv4 address allocation policy, which says that all assignments are valid as long as the original criteria on which the assignment was based are still valid. This implies that if these addresses are being given by the NRAN for the purpose of connecting through the NRAN through its IP network, then they are only valid for that purpose. Now, I'm not going to be a fuddy-duddy about rules here, and it's a rule that gets broken, I will admit, and it is a rule that you can break without anyone really noticing, but it does have implications. So the implications of those, well, my first question is who's working on those implications and who's working on how to deal with this? And I just want to highlight that I think here someone might be missing something. The bandwidth on demand people like myself are working on the bandwidth on demand service itself, working on how to simply implement those circuits. The circuits themselves will run Ethernet or will run some layer 2 protocol, perhaps layer 1 if it's something, well, lower layer obviously. But it is independent of layer 3. You can run any layer 3 protocol you wish over these circuits. And in so doing, thank you, you have, we have removed from ourselves the ability to dictate, if you like, what the layer 3 requirements are and what the layer 3 responsibilities are above that. So if you wish to create an arbitrary connection, the user must then be responsible for their own routing. However, users, in my experience, don't tend to be multi-domain routing experts. You might ask, how do they make sure that the traffic is going in the right direction? And the answer, to be honest, is they employ me to make sure that the traffic is going in the right direction and it's going to JAON instead of to the general internet or to a local internet exchange where appropriate. The RIPE policies, one of the questions I got asked before was, are RIPE looking at this or are RIPE working on this? And as far as I can see, my answer now is the same as it was then. The RIPE policies are already in place to attack this sort of thing, but there is no magic policy button, apart from going back to classical days and very complex routing technology, that will solve this for us. Which means that the users are probably going to end up asking questions if they have unrealistic expectations of what they can do with this service, which is very easy to set up, unless some care is taken beforehand to either make sure that they understand what the implications are of routing on the services they can have, or the service is put in place in advance to make sure they can do what they want, whatever it is that they want. I'm still not quite sure what users want. I haven't met very many of them, at least of this particular service. In an awful lot of cases in HANet, at least, we're looking at intra-institute connections. So these guys are already very, very good, and some of them are in the audience, are already very good at running your own networks, and this is an extra link within your own network. There is no problem there. Where there is a link between multiple networks, we have some trade-offs. So the trade-offs, I've got a bunch of solutions here. They're all fairly naughty, but I wanted to evaluate them in terms of certain criteria. And these are the criteria that I came up with. If you'd like to throw me some more, I mean, these are quite arbitrary. Feel free to throw some more, and we can add them to the list. The first criteria, or the first thing that's probably going to have to give if something else is to be accepted, is does it follow the rules? So, for example, the RIPE rules, the rules of best practice of routing. Are you going to have a little bit of a hack on your routers to make this work? Is it easy for the users to deploy? Is it easy for the operator to support? And is it flexible enough that we can deploy it on an existing network, whatever the existing network happens to be, without further trouble? So, this is a solution that I came up with when this question first came up. What's the user going to do with this link? Assuming they don't want to simply connect two computers together, but want to connect two networks together. Well, there is a correct way to do this. They go to their local internet registry, they ask the internet registry to go to the regional registry, get them an AS number, get them plenty of PI space, provider-independent space, renumber their entire networks into this PI space, run BGP to their campus network, and run BGP from the campus network to the NRAN, and that transits on. That, in many cases, may well work, and in many cases I think isn't going to be a runner. It is in some ways the only... It's a perfect way to do this in the sense that it is the one that will get the most flexible results. But it doesn't fare very well when you look at the ease of deployment or ease of support on the part of anyone involved. It's certainly not flexible to implement in existing places. Users hate renumbering. Everyone hates renumbering. Everyone will do anything they can to avoid renumbering as far as I can see. And one biggie here is that it doesn't fit very well with the idea of on-demand circuits if you then have to bring a very complex routing on routers that might not even exist at the moment, where they've not been needed before, which requires quite complex expertise. But if you were to try and do this in an IPv6 world, you can't get IPv6 PI space. And end-user networks are at the minute, by policies, expressly forbidden from getting routable space on the IPv6 internet. Again, another can of worms. It's one I'll rant about at length later on at dinner if anyone wants to talk about it. It may be changing, but it is still the case that this sort of behaviour is discouraged for a reason, and the reason is no one really wants to go back to the days of the swamp. The next easy one that everyone always comes up with, and I think this is probably the most likely one, is use private address space, RFC 1918 space. And again, if you have a pair of machines that you wish to connect together, and a grand total of 2 machines at 2 different locations that require 1 link between them, this may well be the way to go. You have a non-routed link between the 2 with some private address space on it. And if you wish to contact the other machine, fantastic, you use the private address in that case. If you wish to connect 2 networks together, then again you must renumber the networks themselves into 1918 space and use some sort of network address translation or similar to actually reach the outside network. Problems with this? Well, it means your networks go from perhaps being fully connected or fully addressable to no longer being fully addressable except by the other side. It does remove any hope of connecting directly to the rest of the internet, and any applications that require end-to-end internet access beyond the other side connected by the bandwidth-on-demand service won't work anymore unless you work through a NAT. And you have to renumber. No one likes that. Third possible solution is to keep using your existing subnets, where you have subnets, and directly connect the networks. So this assumes, for a start, that there is some subnetting already in place in the campus, which happens to coincide exactly to the network that you wish to route over the bandwidth-on-demand service, and happens to coincide exactly with networks that you do not wish to route over the bandwidth-on-demand service. You set on the hosts a static route, which points for those very specific addresses at the remote site down the bandwidth-on-demand service and nowhere else. A couple of problems with this. This is actually perhaps, in some ways, the most elegant one. It probably solves the most problems in the easiest way without causing the user the most hassle, but it can fail in interesting manners. As far as I can see, there is no sensible way to ensure failover in this instance, so that you continue to use your old IP addresses, but it breaks the conditions for the IP allocation, which is fine as far as it goes. But the implication of that is if your bandwidth-on-demand service goes down for some reason and you wish to continue to use a regular internet, you are no longer following the rules which the regular internet routing policies expect you to, so they will not react in the manner that you wish them to, which means you lose failover, at least. It is difficult to manage as well. You're potentially, if you plug it into the wrong port or give the wrong configuration or reload the switch at the wrong time, you're potentially bridging 2 campus networks. And I had hoped to see more people wince at that than actually did. It is putting interesting failure scenarios in the hands of users who probably don't have the access to fix those problems if something goes wrong. We have to give them a port which perhaps has more capability than is necessary to provide the service without giving the ability and the responsibility to fix problems that may occur because of that. And the last one is where you don't have a subnet. This is related to the previous one. Create a subnet, so renumber into the subnet, route the subnet, configure some sort of routing between the campuses, perhaps dynamic, perhaps not. Dynamic gets you quite a lot. Dynamic actually gets you failover. And, well, where does this one go? Unless you go all the way back and look for provider-independent space, then you're still breaking the conditions for IP allocation. So you might get it to work. It can still be a little bit iffy. It does require some routing knowledge on the part of the whoever's implementing it, which is probably going to end up being the user. And it also implies, I think, some routing knowledge on the part of the hosts, which is an interesting problem to try and solve. Hosts, we have routers for a reason. They run dynamic routing protocols and they have fairly extensive routing tables. And if we go back to asking the hosts to implement routing, then it becomes very difficult to enforce any kind of IP policy there. And it also becomes very difficult to enforce any kind of backup unless you implement very complex routing policies with complex protocols in place that no one these days really wants to run on a host. So approaching the end now here. There are the, if you like, the sensible answers that everyone always comes up with. I've been casting around for other options here, and there are a few, but they're all quite specialist. It's been pointed out to me that IPv6, if the user can run their applications over IPv6, which already, at the moment at least, gives us a smaller user base and a smaller application base, then this can give us a much freer hand in solving this problem. So while you might have some difficulty getting, for example, provider-independent address space that you can route arbitrarily, you can use multiple IP addresses, or IPv6 addresses, I should say, on any given interface. You can use reasonably complex source address selection algorithms to decide, based on your application, which route you want to take, which address you want to use, which has implications for the route that the traffic will take on the way back. Which is actually all very well. It's actually very good, and I think this is probably the most elegant way out of this if the application is supported, but the application has been supported. So that now puts a very great responsibility both on the user and on the developer of the application to write their applications with the service in mind. This can be combined then with regular VLANs. So you might have multiple interfaces, if you like. You can implement this physically, or have a single interface in the host, which has access to multiple VLANs, one of which is connected to the bandwidth on demand service, one of which is connected to the regular campus network. And the host then chooses which VLAN it should route through and which address is appropriate. This can be implemented just as well as IPv4 as it can in IPv6. I think the tools are neat in IPv6 because it was developed with, in some ways, this kind of application, or at least strange multi-homing applications in mind. So the toolkit's probably better able to handle this kind of thing. But in principle, there will be no problem implementing this in IPv4 as well. So I looked at this and I came to the end of it and I went, oh God, I have to stand up in front of a crowd of people and present this because the solutions to my mind aren't very satisfactory. None of them solve all the problems. And the ones that solve most of the problems are quite tedious or quite difficult to implement. So one of the questions that I have arising from this, and I'll be delighted to hear some answers as well as questions when I put down the microphone, is do we expect the bandwidth on demand services to be used like this? So I'm glad to be able to ask this room rather than the room with JRA 3 people in it, because this lets me ask people who I haven't been speaking to before, if you are implementing a bandwidth on demand service, if you're looking for a layer 2 service to somewhere else, is it going to be implemented like this? Not a lot of HEN customers, the answer is no. They're going to implement it within their own campus networks, and they're already well able to solve that problem. Well, are there applications out there which have the kind of complexity that we're going to have to deal with here? The tools, as I say, are there to handle this. The right policies are in place. The addresses can be got if you need it. But on our part, between the NRENs and their customers, this isn't really a problem we've had to solve on a large scale before, and we want to have the ability to implement it on a large scale. So for the first time, the conclusion is that the network itself will be more dynamic than the addressing of the network. And that's where I ended. Thank you very much.
Do we have any couple of questions for Dave and Martin?
Dave, hi. I just wanted to clarify something. You're talking about following the rules that RIPE lay down for the use of the IP addresses. So just so I can get it clear in my mind, you're saying that at the point at which you link to remote sites with a layer 2 circuit, as it were, off the internet, then at that point you are breaking the rules of the use of those addresses that you were assigned. Is that the underlying point, or have I missed something out there?
It's a little more complex than that. The RIPE rules are in many ways quite lightweight, and I think much lighter than a lot of people believe. RIPE gets a blame for a lot of things which it doesn't quite deserve, but it's the RIPE rules require that the address space allocation is justified over a certain time scale. And so you need to explain the reasons for having those addresses assigned, and you need to explain what you're going to do with them. It is the case, I think, in the past, in networks that I have seen, that the IP addresses were assigned for a particular purpose, which was to route through the National Research Network. And that was the justification, and not that the right police are going to batter people's heads if that changes, but the routing for those addresses was set up on the same assumption. So if you no longer use the addresses in the way in which they were assigned for, then you are also implementing those addresses within a routing policy that is not the one that was originally had in mind when it was set up. And so unless you make extensive changes to your routing, it's probably not going to do exactly what you expect. It will probably work when you implement it, when you plug it in and make something happen, and then something will change, some link will fail or some router will die, and it will not have the effects that you expected.
Thanks.
Any other questions? All right, thanks again, Dave. Our next speaker is Martin Koopmans, who is going to talk about the SurfNet detective.
Thank you. I've called the presentation a network detective for the rest of us because I'm on. Now it's on? No? And now? And again? Yes? Okay. I've called the presentation a network detective for the rest of us because it's not only what we have built that we've got a network detective, but it's also something that you can reuse. Thank you. So I'm hoping to show you not only what the detective is and what it can do, but how you can build a detective of your own. Was that a detective? Sorry? Was that a detective? No, that was just me when I had more hair in the grass. The outline is, I have a brief outline of the components of the detective, and then mainly it's demo, 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 and demo. If there's time left, some project trivia, and then there's time for questions. Well, what is the detective? This is how I wrote it down more or less in a project proposal. And I think it's better to show you than to read this. The components of the detective are, there are quite some components. We have the client. The client typically does all sorts of tests, and normally it uses a test server or more test servers to test again. And in our case, you can choose to log every result you get in a central database. This is very handy because you can gather long-term statistics. You can have a help desk, and you can have an end-user portal, and they can all use the same set of data. Also, we have the web-based knowledge base that's integrated with the detective. I will show you that later. And it means that you can keep, for simple problems, you can keep the end users away from your help desk. The other big component, and I think that's, if you find a concept like the detective interesting, is the builder portal, which is a completely web-based interface that you can use to get your own detective, with your own tests, with your own skin. You can get all the same software as a download after you've filled in some forms from the build portal. I will hopefully show you that as well. Well, I would like to demo the client, the knowledge base, the end user portal, and the builder in this order. So I'd better start doing that then. Actually, so this is the detective. We have this splash screen. You saw the SurfNet logo on top. That one is skinnable, so you can replace that with a logo of your own. You see all sorts of tests. We have test groups, so you can group tests. For example, you can watch the IPv6 test, which is right now only connectivity for us. You can look at the default set of tests, which is IPv4, NAT, TCP bandwidth, web download. This is all in Dutch. One of the nice things about the detectives as well is it's multilingual. So we can switch to English. we'll have to restart, getting that installation. There you go, everything in English. Now, if I want some information about IPv4 connectivity tests, I just click on it, and to the right you get some short description about what the test will do for you. If you want to know more, you can click here, and a web browser will start. And you will go to our knowledge base. Our knowledge base is bilingual. We have all the articles in Dutch and in English as well. Of course, you can run some tests. I think that's nice to do. We'll select none. And one of the things we also have is dependency checking between tests. For example, if you want to do a net test to see if somebody is behind net, you have to check IPv4 connectivity first. Because there's not much use in checking net if you don't have IPv4 connectivity. So we'll do that. And we're not behind net, we have, well, you can see it here. You can click on the details tab. Again, you get some explanation, and you get a link to the knowledge base. And the link changes depending on the result of the test. If your test is successful, you go to a different article than when it has failed. If the test has failed, you can give some extra explanations about why it may have gone wrong, what you can do yourself to correct it. Here in the corner, you see test repetition, and this is a feature which is especially handy when you're working with a set of power users. We have used this extensively in ADSL2 Plus tests, and we had a set of users that were testing the ADSL2 links. We gave them the detector, and they said, well, you click here, you say test every 30 minutes, and by the way, set it up as a service. So it just installs as a service in the background, and every 30 minutes all the tests are run, and we get all the results in the central database, and after a few weeks we see how the ADSL2 Plus performance is in various aspects. We won't do that here, we won't do that now as a service. And this is one of the coolest features, and also I think very well hidden of the detective, is we have a little lookup service, and if you have a name filled in the options tab, I don't have it here, but I can do that. Then you can look a user up. And of course I don't find myself, that's a demo effect, but normally you would see my IP address here. And I can do a bandwidth test from me to you directly, and all other sorts of tests as well. That's quite handy when you're video conferencing and it does not work. Do you have enough bandwidth? How's your, well, etc., etc. So I think that's more or less the client. But we have the about box, of course, with our logo. This is also all skinnable. I'll show you that in a minute. I mentioned the knowledge base. I will briefly show you that as well. You can see we have quite a lot of articles, with categories, firewalls, the download test. Here you see why has it failed, what's the relationship between kilobit, kilobyte, and megabit. This is typically what an end user asks. How do I interpret the results of the web download test, etc., etc. And what's also nice, you can search the knowledge base, for example, for video. And then you get back all the articles related to video. And the nice thing is that we've developed all this content ourselves, so if you want to deploy the detective yourself, you can just use both the detective and the knowledge base articles as well. I also mentioned that everything is logged in, that you can use an end user portal. We have an end user portal. And well, obviously this is not me, and you also saw that I didn't have to log in. Why? We have the end user portal integrated with our local single sign-on infrastructure, A-Select. And the integration is ready, but it is not integrated in the deployment I'm showing you right now. So you just see an arbitrary user. And here you see the details of sessions. You can choose show all sessions. and we can log in, zoom in, and get more details of the sessions. So an end user can gather long-term statistics of his own performance if he wants to. And you can think of a similar interface for a help desk or an institution itself, just to see what's happening and how the users are doing. So if somebody's calling, I cannot watch the video online, you say, okay, run the detective, what's your username, you can watch in the database and see what's wrong. Now for the, I think, most interesting part, the detective builder. This is where you actually build a detective. It's nothing more than filling in a form and clicking on build. One of the nicest features about the Builder Portal is that you can share whatever profile you make. Actually, you see here the March 2006 profile. This is a profile from Internet 2. They have deployed this version of Detective last week as well. And while learning how to use the portal and what all the configuration parameters were meaning, they shared their configuration with me so that I could help them. I will show you the ServNet production configuration. You see the name here. You see various things I can edit. I will show you later. There's a list of names that we will use in the test for DNS speed lookup. And there's some extras room for wizard scripts, which we're not using right now. First thing, I'll do this from bottom up, which is, in my opinion, a good approach anyway. You saw the testing groups where I had the default IPv4, IPv6, the oldie tests. And what you can do here is you can define the groups. You can add a new group, you can give them names. You can assign tests to the groups. For example, if you look at the IPv4 tests, you see that it's everything basically besides the IPv6 tests. IPv6 tests the other way around. The default tests are just 5 or 6 tests that our marketing people find most important for end users. So here you assign which test to show where. You can add new groups and you can reassign, etc., etc. You can edit the client skin. This is actually quite funny because the ServNet templates have changed a few weeks ago. So I don't know if anybody of you knows the green bars that we used to have. And I was just about to deploy version 3, and then my colleague said, well, we should, get the new logos in. So we did. You can just upload your own image, provided that it is a specified size. You can upload it. You can even upload the icon, and it gets all in the build. So you get your own branding there. What you can also do, some tests require extra files. You can define your own tests. I will show you that in a minute. They require extra executables. For example, say that you want to have an H323 test, which we don't have in the detective, and you want to use a command line tool for doing some tests. You can add it to the installer here. Then it gets stored in your profile. Okay, I haven't done anything. Then the configuration for the client and the server. Of course, you have a client and server configuration that match. So the server configuration is quite simple. It's basically a set of ports for the different services for tests to listen to. And one of the nice things about a detective is it can do load balancing. If you have a bandwidth tests and you have a reasonable amount of users doing bandwidth tests, you want to spread the load, and you can tell what the list of servers is, where to send the requests. All the other things are not so exciting. It's the IPv4, IPv6 multicast group, the time to live, etc., etc. And now we get to by far the most complicated part of the configuration. Is the client. First thing you have to say for the client is, well, where do you post your results to? Where's the interface to the database? And we've chosen to do this very simple. It's just a CGI script on a web server that posts the results to the database. So you give a URI for the result script. The other thing is, we have an auto-update functionality, and the auto-update functionality works quite simple. You just put a set of auto-update files on a web server. You have to indicate where you will put the auto-update files, and of course the contact info. iBirth server discovering. This is basically the dispatch server. This is the load balancer. So this is where you initially connect as a client. And then per test you have the usual suspects as configuration parameters. For IPv4 connectivity, you try to do a ping, an echo, or otherwise an HTTP download. Why some firewalls block ICMP traffic, we've learned. Every test has an entry which is called the knowledge base URL, and that the knowledge base URL here is not the knowledge base you saw, which is web-based, but is a little text file on a website that refers to the knowledge base for the different set of results. I will show you a text file in just a minute. The IPv6 connectivity test, well, it's basically the same. For the knowledge base, you will see that everywhere. The host to ping. We have a trace route test, which does a trace route to a well-known host. It doesn't show the results to the end user, but it posts them to the database. We also have one for IPv6. We have a routing information test, which basically posts your routing table of your local machine to the central database. The DNS performance test, which tests all the names you saw in the first screen, all the sites. The net test checks if the local IP you think you're having is the same that we're seeing from the outside. The on-demand iBirth server is the iBirth server that the client is using when you're doing a peer-to-peer test. And what port should you listen? We have a simple port scan test where you can define a number of ports to be scanned. We have this is quite good. We have a Nessus test as well for security, so you can have the detective trigger a remote Nessus scan on your PC. We're not deploying that right now, but it is available. And what happens is a scan is being done, and after some time you will get an email with a link to the results. We have IPv4 and IPv6 multicast. I think IPv6 multicast is not working actually right now. TCP bandwidth test, where you can choose dual or alternate mode. The dual mode is that you're trying to do the bandwidth test at the same time. And alternate is first upstream and then downstream. We also do a HTTP download test because a lot of people are just doing downloads from the web. So that's quite important to know. We used to have an FTP download test for ADSL2 tests, but nobody's using it anymore. IPv4 network test, which is basically a whois query and a match on the AS name. We have inbound and outbound TCP port reachability, so you see can you reach those ports outbound and inbound. And for example, outbound, I chose the video portal for SurfNet because that's one of the most widely used applications where the most problems are. So we see if you can connect to all the ports. We have the same thing for UDP, but then it's inbound. Can you reach well-known UDP ports? Actually, a colleague of mine asked during the lunch break, can you add the well-known ports for SIP? We have a firewall filter detection test, a UDP throughput, UDP streaming. UDP streaming is basically the same as UDP throughput, but it's not go as fast as you like, but go in a controlled manner. So go for 64 kilobits or what have you. And then this one. This is basically everything we don't have. This is quite an important test. What you can do is you can add extra files to the detector. I showed you that one or two screens earlier. And here you can call them. You can define, okay, this is a command line, call it, and when the results come back in some well-defined format, show it in the display of the detector. So it looks user-friendly. And you can add all the infrastructure with the knowledge base, the results failed or succeeded. And then finally, we also have a thing which is called extended test scripting. You can imagine that doing a net test is nice, and doing a UDP port reachability test is nice, and doing a bandwidth test is nice. But what I want to show my end user is, can I watch video? So what you can do is you can script the detective. You can write a short text file included as well, and say, okay, I have a test that's called the video test. And actually it consists of the net tests, and it consists of the UDP throughput test, which has at least 1 megabit bandwidth, and you have to have these ports reachable, and then you can watch video. I will show you a very simple extended test script in a minute. So then you're done. There's one thing left, and that's build. And when you press build, it takes a few seconds. Right now it's doing the on-demand build. It includes all the files we've just uploaded and things we've specified, and you will get a setup.x back you can just install on your PC. So there you have it. I can just put it on my desktop. Yes, I want to. And you see those logos, etc., etc. And the same thing works for the server as well. And I can also download my auto-update file. So once I've made an initial deployment and I change the configuration or I add an extra test, I can just download auto-update files, put them on my web server, and everybody that has the detective running just gets a message, there are updates. Actually, if I install this one, it will demonstrate just that. You see, because there were auto updates available for this version. It downloads them if you want to. You can start over. Now, I promised you two more things. First thing was the very simple knowledge base. Okay. I'll just open that in Notepad. It doesn't work as nice. Oh. This is better. This has a pretty strict format, and you will see all the things you saw on the right side. The test title, you will see the short description, you see the module test description, but you will also see the knowledge base URI. And what is the text when the result when it's failed, or when it fails, what's the URI, and when it succeeds, what's the URI, and what's the text. You can change all this. The advantage of putting this in a separate text file is that when there's a new knowledge base article, as an engineer, I don't have to go through all the trouble of making a new build, but my colleague from the marketing department can just adapt this text file on a web server. And I have another one, which is called the extended test scripting. This is one we used in the ADSL 2+ test as well. The problem there was that we had to. We saw that UDP up to a certain bandwidth for some users went okay, and after that it collapsed. So what we did is we defined an extended test with 300 kilobits, 600 kilobits, up to 8 megabits, and we defined here we defined a test. UDP 300 kilobits is just a UDP streaming test with its parameter, the bandwidth 300K, and a test duration of 15 seconds. The funny thing is, any new test you develop for the detective is automatically scriptable. And when you get back a result, you can have some sort of simple if then succeed fails, and it displays different messages. And you can also set the URIs there. So you can add your own tests, or you can group them there as well. I think this is all I had to demonstrate. I don't know, how much time have I got? Time for questions?
Oh yeah, definitely time for questions.
Okay. Are there any questions? Yes.
Hello? Okay, you can hear me.
Yeah.
So you mentioned several times video as an example of something that needed to be tested. And I've played around with the detective. It's been a while, but it's and I'm very impressed with it. But when I looked at it, it didn't sort of do the right thing for a video, for me at least, because very often protocols like SIP and H323, it's not enough just to have a throughput test or jitter or stuff like that. You also need to test whether you get the right ports opened in your firewall. So does the current version of the detective address that?
depends on whether it's a fixed port or if it's negotiated. Every
It's
time.
negotiated.
Yeah. Okay. So.
So actually, what
Yeah.
would be really, really nice to have was something inside the detective that can do an actual H323 call to the detective server, or SIP call, or RTSP.
The point is that that's where I said one of the most powerful tests is the external command test. So if you have
the what?
We have an external command test.
Yes.
If you have a command line tool that can do that, and there are a lot of tools around for all the testing suites for different. You can just integrate them and get them back in the user interface. The problem here is that I cannot solve every testing problem for everybody in the world. What I can do is provide you with a framework where you can just plug in your own extra tests and have all the benefits of central logging, the user data, the knowledge base, etc., and the other tests that you can use. So, and also it differs per service. So you can imagine with a portal, it's quite easy building a new detective that you just build a video detective, which has a totally different set of requirements. So yeah, the short answer is no, it's not in there. The longer answer
But we can
is,
extend it.
You're more than welcome to extend it and share. With the rest
So a related question is, you mentioned a firewall test.
Yeah.
What exactly does that do? That just tests for specific ports.
It tests for specific ports if you can. It's basically it's based on the port scan and the inbound and outbound port reachability test.
Okay.
So it's a firewall detection. A firewall indication would have been better. But you don't want to bother the end user with that.
Thanks.
Okay. Any more questions? Case. Oh yeah.
I don't need to ask the question.
Yeah. We're working on it. No, really. We have an OS 10. Yeah. Case is asking, as always, is there a version for the Macintosh? We have a beta, and Case is not the only one I'm seeing. We have a beta version of the OS 10 SDK for the programming language we use. And I've asked our developer. Actually, this has been developed in Italy. That's quite nice to tell. And he's working on it this week to research if it's viable to get it working. We expect to have it working by the end of the year. It shouldn't be that hard because we have it working on Windows, Linux, and FreeBSD. And FreeBSD is pretty close in the system calls to the Macintosh. So we expect to, coming soon. Yeah.
Hi. I come from a country which is not included in the language selection. Is it possible to upload an additional language setup?
Basically, how the detective works is internally you have a localization file, a catalog, and we can give you the catalog because right now actually we have 5 languages there, but only Italian because it's developed here. Dutch and English are really up to date. You can I can give you the catalog and you can you can translate all the entries from English to your language, and we upload it, and then there's another language in the detective.
Okay. An additional question. You mentioned that it's possible to extend the testability functionalities by just writing an external script that writes.
Yeah.
So in that case, do the pre-existing users should download a new version of the?
No. That's also you give a URI for the extended test script. You put it on a web server, the extended test script, and you have to sign it. So not anybody can just put up a script and get your users to do some sort of DDoS attack. So you have to sign it. And you can change the URI via the auto update. So your existing users do not have to change anything there.
The last functionality you mentioned that the signature. I can recall is in your presentation in the part where it was 4A signature or something like that. Mentioned.
Yeah.
Okay.
We have a tool that generates a public-private key pair, and you just paste it there, and that the key gets embedded in the executable as well, though. So it knows how to check.
Okay, thank you very much.
Last question back in the corner there.
Are the basic log files that the detective generates in its tests available via some protocols? And also are the results of the tests available via some protocol? Is there a schema defined that might capture the data for query, etc.?
Well, the data is available in two places. Actually, Internet 2 had a very good suggestion to create local logs as well. So there's a local log file. For every different test, there's a different log file. It's just text-based. And the server is just a MySQL database with a well-defined schema. So from there on, you can generate all other kinds of log files, and you can generate all kinds of view. Right now, we have an end-user portal that integrates with single sign-on solutions, and we have for our own use a server view on it. So we can give that to a help desk. But you can do anything with it that you like, provided that you use a logging database.
All right.
I'm more than happy to answer questions, otherwise.
That gives me another insight from Ken's comment. I mean, would you ever thought of reporting back using a well-known schema? Like, I mean, you can extend the global grids from NMWG schema to match those results, and those results could be available. I mean, to could become, let's say, a global, let's say, repository for test for.
Yeah, well, but the thing is, there's we thought about it, and we decided to keep it as lean as possible because, well, there's a very de facto standard which is called SQL, and almost everybody understands it on how to query a user database. So, yeah, we thought about it and decided, well, just as simple as possible, post via CGI script.
Okay, let's thank Martin for his talk. And I'll remind you again to fill out the evaluation forms online. And I'll introduce our next speaker, Anand Patil from Dante, who will give his presentation on the advanced multi-domain provisioning system.
Good afternoon. My name is Anand Patil, and I work for Dante. And I will be giving my talk on advanced multi-domain provisioning system. This is a brief overview of what I will be presenting today. I will try to tell you about why this is necessary, what we have done so far, and where it's heading.
Good afternoon.
A brief introduction of GN2. This is the political propaganda that we always have to do. GN2 is the 7th generation of the European Research Network. In addition to giving the normal services that we were providing in the previous versions, in this time in GN2 we are going to offer more value-added services. For example, there will be new layer 1 and layer 2 point-to-point services switched. So the focus is about giving more value-added services, and one of the services that we are offering is the PACE activity that we have, the SA3. This is about performance and allocated capacity for end users, which is dealing with the end-to-end quality of service provisioning. Right, so what is the problem? The problem that we are trying to solve is the fact that whenever any user wants an end-to-end service, typically they have to contact all the domains that are involved in this end-to-end path. So in this example here, if this user wants to have a service across these 3 domains, he will have to contact the domain 1, domain 2, domain 3 separately and ask for this service. In addition to that, there has to be some stitching that will have to be done at the edges of these domains. Therefore, these domains will have to communicate with each other and tell a certain amount of details across to stitch the service. This is what we are trying to solve, and the rough approach is something like this, that what we ideally want to do is for the user to contact a single point. There has to be a single point of contact for the user, and the user should not really need to know how many domains are there, which path does it take, which network does it go through, and a single service should be able to go across domains and provide an end-to-end service. That is the problem space that we are trying to achieve. What is our motivation? Normally, most of the clients are well happy with the best effort service that you have. But there are certain projects which require a high-performance network. They would like to have more guarantees on certain metrics, like bandwidth, maybe delay, jitter, packet loss. Well, there are always clients who can afford dedicated point-to-point and end-to-end circuits. But then not everybody can do that. There are, of course, some customers who will be wanting to use the normal IP and will not really pay for a dedicated circuit. And there is always a cost versus performance issues involved. In theory, there are a lot of frameworks for IP quality of service, but there are very few which have reached production quality. That means there are very few of them which are offering an end-to-end quality of service in their production networks. And again, if there are these kind of systems, they are usually heterogeneous, which means they don't really need to talk to each other. And they exist only at intra-domain level. That means it can be done only at a single domain level. There is no real practical unified end-to-end model. And of course, finally what happens is that if you want this end-to-end service, it takes a lot of time. That means you have to contact each network, send them emails or call them up, and the whole lead time for provisioning is quite a lot. Of course, users will definitely benefit from a single service point where they don't have to contact multiple domains. This is exactly what AMS is trying to do. We are trying to build a practical, federated services which will realize this automated end-to-end QoS. Giving a very slight amount of background, what we started off doing was we had in GN Network a premium IP provisioning system. So what we are trying to do is to build upon what we already had and will not try to reinvent the wheel. In theory, what basically happens is that we are trying to regulate the amount of IP traffic, or prioritized IP traffic that goes across our domain. This is basically a model that was proposed by the Sequent project, which was done a couple of years ago. And what has been proposed is that if you can give differentiated service to a regulated amount of traffic, then you can offer certain quality of service that can be given with an SLA. In our case, advanced doesn't really mean advanced as in futuristic. It means something that you can book in advance. Unlike, say, for example, what GRE3 is doing is bandwidth on demand, which is instantaneous. It's more like saying what you want now. What we are trying to do is book something that is in advance. And this really causes a little bit of an issue because, well, network conditions can change. Things can change, and you cannot predict everything up in right now. So the advance is a bit of an importance there. Multi-domain, again, as I was emphasizing, implies that you can have a single request, and the single request can go across multiple domains and book an end-to-end path. What we are trying to do is to take a pragmatic approach. If you take one kind of a short approach where you want to build a whole and a perfect system, it wouldn't work. What we are trying to do is to take an incremental approach where we understand that networks today have certain limitations. Not everything is ideal. So we would like to build a system that can work today with today's network constraints, and therefore it will have certain assumptions, like certain networks may not have premium IP. So we are trying to cater for that if you are over-provisioned, and even if you are over-provisioned and you can give at least qualitative guarantees over metrics, we are trying to take an inclusive approach where you can take part in the system. Other assumptions we make is, there are a lot of other assumptions, and these assumptions will kind of go away as networks and their services evolve. So when networks move towards the ideal situation, we can remove all these assumptions from our software, and then it will move towards the ideal state. Currently, it's being developed by these partners that I've mentioned here from GRNet, Poland, and Dante. Right. We are trying to follow a service-oriented architecture here. Basically, this means that it's a multi-domain, peer-to-peer federated architecture. There is no single entity which is controlling everything. And this scales very well, for one thing, and networks are very happy to deploy something that is in their control. They would not like to see some super user controlling resources within their domain. And that's something which is very important for us, and which is why we chose this kind of a peer-to-peer architecture. Any other architecture would have been good to have, but nobody would have really taken it up. We have defined all our interfaces in XML, which leads to a good paradigm of web services. Another thing that happens with service-oriented architecture is that we build our services with smaller services. So we have a lot of component services which put together create the whole system. And then it leads to easy integration with existing components that domains may have. What this basically means is that, for example, if you have your own database or your own system to do your own single domain reservations, you could integrate that with the whole federation, and you don't have to necessarily take the reference implementations. As an example, we have systems from GRNet, the ANS system, which is their tool to reserve premium IP, and we can just take that and use that in our system. We're not forcing them to say that you have to take our system and work with it. We have done a reference implementation in Java, so of course everybody is free to take that, but we are also giving the freedom to our users to say that, well, if you don't want to take our implementation, you are free to develop your own. All you have to do is to implement these standardized interfaces. Another highlight of the architecture is that to keep the model scalable, we are trying to not build a full mesh of services, which means that each domain is aware only about its neighbor. If you create a full mesh, what happens is that when a new domain joins, everybody has to be informed, and agreements will have to be made with the whole of the domain, all of the federation. What happens here is that when a new domain joins, it only creates agreements with its own neighbors, and it joins the federation. Other people do not have to know that a new domain has joined, and things will just work. Right. Few design considerations. We had to come up with an asynchronous user interface. This was because the amount of domains that you go through and amount of time that it takes for a request to be provisioned takes a considerable amount of time, and this can go across your normal HTTP timeouts. So the user interface is asynchronous. That means you make a request, you will get an instantaneous response back saying that here is the service handle, I am trying to provision your request. And after some time, you can come back and query with the same service handle to check whether your request has been accepted or not. We are using traceroute to find paths and next hop, and this is basically because this is what is ideally possible today. We are thinking of a BGP as well, and of course, this does lead to some issues and problems that we have. In our phase 1 approach, we said that, okay, let's try to do with traceroute. We analyze the traceroutes, and from that we can determine what is the next hop, and therefore which is the next system that we need to contact, and what would be the ingress and egress at the borders that we have. We also decided on going for one-phase commit on transaction management, because of course when you have multiple domains involved, you have this whole concept of transaction management. When you start a transaction from domain 1, if it succeeds, the next domain says, I don't have enough bandwidth left, then you have to go and cancel the reservation from the first domain. The ideal way of doing this is a two-phase commit, which is a very well-understood problem space, but that's very heavy. Therefore, we decided to go with the one-phase commit, where if something goes wrong, then you'll come back and roll back the service. We also had a concept of establishing trust relationship between neighbors. This, as I was explaining before, is the fact that you only need to know your neighbors, but you need to trust them. Therefore, for security purposes, you will have to probably exchange keys or certificates to ensure that, well, you are allowed to talk to your neighbor. We also have come with a reusable component called forwarding layer for at a application layer forwarding messages for transporting payloads between two web services. So this is a very generic component which can take any message and transport it across towards your destination and give it to the service that you want to give it to, and you don't have to know where the service is, in which domain it is there a path to it or not. All that will be done by this message transport service that we have developed, and this can be used by other people as well. Similarly, we have come up with a period database, which is about abstract resource management. We found that there is a very common problem that you have a resource and it has to be managed across time. It could be something as simple as a meeting room which has got different bookings on different time levels, or it could be a network pipe which needs to be booked on different times. Therefore, this is something that we have come up with, again, a reusable component, which you have an abstract resource and we have a complete set of APIs to manage it across timelines. Another important design feature was accurate rejection reason reporting. We found that if you cannot tell, if something fails, you need to exactly tell the user what went wrong. So we are able to tell in the software that you did not get this service because in this domain, on this interface between these two routers, there wasn't enough bandwidth available on that day. This helps the user because then they may want to change their request. If they know that, well, if I could get 90 instead of 100, if I'm told that, I may change my request. If you don't tell this, then the user has no clue about why the request had failed, which domain it failed in, and what should I do about it now. Another design feature we tried to put in was that we did not want to go for automatic network element configuration. This was because if you did that, a lot of networks would have told us, well, we don't want your software to touch our network equipment. Therefore, the model that we have come up with is to say that, well, there are two ways of doing it. There is a switch. If you turn it on, we can go and configure your routers. But if If you don't want that to be done, you can turn off the switch, and what will happen is that we will send an email out to your NOC or to a designated email address, which will contain the details of what needs to be done. We can mail you the configuration that needs to be applied, and then you can check, verify, and do it manually. We have about 4 or 5 services defined here. We have an inter-domain provisioning system, which is the multi-domain system which talks between multiple domains. We have an intra-domain provisioning system, which is what happens within a single domain. It's concerned with all the things that happen within a single domain. We have a network information service, or the pathfinder service as we call it, which is responsible for finding paths. By doing this, we have ensured that you can plug in your own service about pathfinding, whether it is trace routes or BGP or any other technique that can be done. And in the future, we would also be coming up with configuration service, which will automatically configure routers, a policy service, which will dictate policy about which network wants to give what resource to which user group. And of course, we are also going to integrate with the GRFI's Edugain AA service at some point in time. Therefore, we have about a few interfaces. We have the inter-domain control plane, which is the ENNI. We have an inter-domain control plane. We have a client interface and the network information service interface. This is on a very high level how the architecture works. What normally happens is that a user will make a request. Either it could be a GUI kind of a user, or it could be software clients, for example, the EGE grid middleware. These clients can send a request to the inter-domain service. What the inter-domain service does is first it contacts the intra-domain service to find whether it is possible to make the reservation in your own domain. Once this is successful, the intra-domain service will respond back and say, yes, it is possible, and then the message will be sent across with this interface across to the peer system. And the same box is here, and the process gets repeated on every hop until it reaches a point where there are no more provisioning systems in front of you. And of course, the network information service is used to find which is the next one to be contacted. And then hop by hop, the request goes across multiple domains. In case something goes wrong, a message comes back to the original system that, well, it has failed, and then the first system will then roll back everything. The system would be the transaction manager for this entire transaction, the first system that you have contacted. We also have defined this interface towards configuration, and as I said, we have 2 ways of going down. You can do an automatic configuration if you choose to, or what is most common now is to send an email to the network operations center, and they are going to do a manual configuration of the network elements. What goes wrong with this, or the issue with this, is that it introduces a lead time. This is something that will take time. It could be up to 1 working day, 2 working days, depending upon the network policy. And this is what causes problems with the users, that if somebody says that I want something now, I can't wait for 2 days. So what's our current status? Currently, we are doing this on bandwidth only, which means that when we provision a link or we provision the service, we only check whether there is enough available bandwidth. In future, we should be able to do this on other metrics. It could be, well, you can check on delay. The user could say that, well, I want a total delay of 60 milliseconds, and you should not go beyond that. So we will have to then appropriately choose paths between, on our domain or the multi-domain paths, ensuring that the total delay does not exceed the given value. It could be done on jitter, it could be done on different network metrics. This is something that has been built in, but what needs to be done is to populate these values. We do not really have very, very accurate values for all these things, and concatenation of metrics across domains is also another research issue which GRA1 is tackling right now. We have finished our inter-domain tests, so we are able to reserve a path between, say, 5 domains. We have done these tests successfully, and the version 1 of our software was released in December 2005. This includes all the basic functionality about the UI, the inter-domain, intra-domain, pathfinding, and everything. Right now, we are in this bug fixing and enhancement mode, especially user interface, because people want more and more better user interfaces. Our policy and configuration services are under development. And we have very simplified AA services right now. We are waiting for GRFI integration. We also are doing interoperability tests with the GRNet ANS tool, which is the GRNet single domain tool, and along with ESNet, which is in America about Oscars, and the Internet to Brew tools. These are the tools that we know exist on a single domain level, and what we are trying to do with them is to offer our multi-domain component to them, and them trying to then interface our multi-domain component with their own existing single domain components. and then trying to make a transatlantic test. This is something that is currently going on. Okay, deployment. We have a test bed deployed in GN2, GRNet, PSNC, and Dante. This is just for people to play around with. The production system is deployed in GN2, as GN2 offers a production premium IP service, and we are able to offer this as a service. We also have a sandbox which you can play around with, and all this is available on our website, again with appropriate access rights. The production system is available to only the authorized users, whereas sandbox is available for anyone to play around with. We are hoping to have a pilot service which will be implemented in GAR, GRNet, and Ukerna. This will be our first real test that you can have an end-to-end service offered. And we are hoping that these networks will join us soon and be able to give us the end-to-end service. And to be honest, we are hoping that the production service should be deployed in all the partner networks, because this is one service we expect that people would like, and we have a software ready for you to use. And we are hoping everybody to deploy. As I said, it is not necessary that you have to have premium IP deployed. Even if you are over-provisioned, you can be in the game. Few issues. We had a lot of problems with trace routes. The simplest problem is it's been blocked. Well, people block trace routes, which causes problems. And then you go into issues about it takes a long time to finish. It goes into all these asterisks that come back, and it takes about 25 hops before you get back the result. So we are trying to move away from trace route and try to do something with BGP or any other technology that we can think of. And this is something that's going to happen in our next version. There is always a problem about multi-homing and asymmetric routing, because whenever you do any kind of a trace route, for example, you assume that the path that you come in on is the same that you're going to go out on. The ingress point is the same as the egress point. So to detect the ingress point, if I do a trace route back to the source, if the routing is not symmetric, that doesn't work. So this is one assumption that we have made right now, that the routing is symmetric. But in the future, this can change. We would like to get away from this assumption. So maybe ingress has to be specified by the domain upstream. And the first domain, the client has to tell what the ingress is, because there's no way for the downstream network to know what the ingress is, because that could be a local routing policy of the upstream domain. Another very practical problem we faced was populating our database. Topology, it can be a very complex issue, and they're very large, especially with backbone topologies. And a lot of manual work had to be done to kind of ensure that this topology data is represented accurately in the database. And we found that it takes a long amount of time, and things keep changing. Therefore, maintenance of this topology as well is something that we need to automate. Right now, in our first phase, this was done manually, and now we are working on writing programs or automated scripts which could, well, without knowing about whether it's a Cisco router or Juniper router or any other router vendor, to go in and extract the topology out and populate the database. This ensures that people are more interested in taking up the service. Of course, the second issue is steady state versus actual topology. There can be transient network failures. For example, if you're doing some trace route or trying to find out the path, at that point in time, if there is a transient failure, you would get a different path. So if I'm booking something for next month, how can I be sure that in next month the topology will look exactly like what is looking right now? Therefore, you have to be very careful about the fact that are you assuming a steady state topology, or are you assuming actual topology at the point in time? Lastly, we have an allocation policy issue as well. Each network will say that, well, I don't want to entertain all the users that the other network may have. Or it could be some grid users, which are, well, in all networks, they have virtual organizations which are present in many domains. And you have to have a fair allocation policy. It could be simply first come, first serve, but then the danger there is that the first person who comes will say, okay, I want all your bandwidth for all the time that you are going to be there. And that's not very easy. Devising a fair policy is an administrative task, but what we are trying to do from a software perspective is to make it easy and provide an infrastructure where different kind of policies can be written and then enforced. As I said, this is something that we will be doing in our phase 2, and we are having people from GRNet working on this. We do have a policy document that has come up. Now we are trying to implement this in software. But the actual values, as to, well, GRNet will give 10 Mbps over a month to EG project is something that the local people have to fill in. Lastly, of course, the lead time. A lot of grid users that we had, it's a very typical use case that they want to do a file replication. When you want to do a file replication, you do not really want to do it 3 days in advance because you don't know where the file is going to be. You only have a virtual file handle. The actual location of the file will be known fairly at runtime. And therefore, the lead time comes into picture. That how can you say 2 weeks or 2 days in advance that this is exactly where the file is going to be, or this is exactly where the job is going to run? Because that's the whole point of the grid, that you want to distribute jobs without knowing where they're going to run. You don't know which CPU cluster is going to be used. Therefore, automatic configuration will help in that respect, that it will bring down the lead time from in the order of say, hours or days to order of minutes, and this will help users who want some services which can be run instantaneously. But again, the problem here is that will networks allow software to configure their equipment? Our future plans, again, as I said, we are going to implement policy. We would like to implement automatic network configuration. Again, depends upon the actual networks. We would like to add NP-less functionality. This is to ensure that if a particular forwarded path is completely booked, you can actually take an alternate path within your own domain. Right now we are trying to do for single domain only, but we can look into multi-domain LSPs with stitching because we have the capability of passing messages between domains. So for example, a LSP label can be forwarded between domains and inter-domain LSP stitching can be done. We would like to integrate with GN2 JRE3, the light path services when they come. We do have a work item to do that. And of course, integration with the AA services that JRE5 will be coming up with. That is something for us in the future to do. And lastly, as I said, since we have a lot of service components, we presume that these service components can be used to build different services. We have a pathfinding service, for example, which can be used to develop a best efforts LSP management. And this can be taken across multiple domains. A lot of different services which can rely on our core services can be done. All right, so in summary, we are developing AMS right now as a part of GN2SA3. This is a multi-domain system which we hopefully bring end-to-end quality of service to people. We are trying to use a service-oriented architecture which will help us to reuse components and services. We have a version 1 that is deployed right now. We have deployed the version as production in GN2, and hopefully we will be having pilots in different networks soon. We are hoping that all the entrants which surround GN2 will be participating in this, whether you have QoS or you are role provisioned, and with that we'll have a full trans-European system. We do have plans to enhance depending upon the feedback that we receive and the plans that I have already told you about. And we are cooperating with different people to have trials. Right? That's about it. If you have any questions.
Yeah, be ready. Try it. Try it.
Do you hear me?
No.
If you
Use the mic.
I try to speak out loud. If you domains which are under your control. Now you hear me. Oh, okay. And you want to know if within these domains you have a specific amount of bandwidth or delay available. How do you check this? That I did not understand. How do you make sure that the bandwidth is available at that point when you need it? Do you check it?
Yes, actually, we have a database. As I said, I was talking about the period database. So we have a database which can keep track of any resource on a timeline basis. So for the entire timeline, we keep track of what on each hop of the network, how much resource is available. For example, what happens is on GN2 network, we have a policy of keeping 10% of the total capacity for premium IP. So if there is a 100 megabit link, then we will have 10 megabit for premium IP. And then on per day, per hop basis, we keep track of what is being used. So at any point in time, we know on a given time period T1 to T2, what is the utilization of premium IP on a hop.
So you are monitoring foreign networks and keep history what is going on in the networks over a period of time.
It's not monitoring. It's about keeping management information. So, for example.
Sorry, yes, I work with. Yeah. Because we're netcasting, we need a mic.
Right. Basically, we are able to keep track of information in terms of what will be. We are not really going into the network and seeing what is happening. It's not the real-time information we are keeping. We are trying to keep what will be done. As in, there is a booking of, say, 10 Mbps. If the next one comes at 15, we just add it up. And we do that on a per hop, per time basis.
And Andrew, tag me in, as it were, and I'll clarify one particular point. It's very important to realize this period database that Anand was talking about, what is being monitored in the case of Géant is only Géant 2. There's one of these databases in every participating domain. So it's a responsibility of each participating domain to keep track of what resource has been requested and has been booked. And then as a new request comes in, then it's checked against what has been previously requested. And only if the new request can be contained within the policy of that network will that domain say, yes, this request is okay, it fits in. It will then forward the request to the next downstream domain. Say, right, can you manage this now? If every single domain in the path can support that request, then the OK will be sent back to the user.
Another question? All right, let's thank Anand, and remember to fill out your evaluation forms.
All right, thank you.
This is real standardization. Yeah. If we all just use Dells, we have no problems here.
So we'll get started with the last parallel session of the day. No. While we wait for the sound person to show up, we will remind everybody to fill out your evaluation forms. Also, remember to wear your badges to the gala evening tonight, so that we can you make sure that's your ticket to get in. And I'll start the session today. The last parallel session this afternoon. We'll have 3 speakers. Our first speaker is Stefan Kraxberger from the Graz University of Technology, and I'll invite him to give his talk.
Thank you. Today I will speak about sum-based lightweight policy verification. So why are we doing this is because we are involved in an EU-funded project called Positive, and in this project we are intended to develop policy-based security tools and framework, as the name itself says, which means we should design automatic tools for describing a network and describing the policies for a network, and also do automatically transformation from these high-level policies and network descriptions to the low-level configurations, and also do the monitoring of these applied policies. So everything which will be developed in this project will be made open source, and currently we have this policy and network description languages, and now we have to find good monitoring tools and verification tools for our policies. So this is a slight overview. On the left-hand side, you see the security description policy and the network description language, and this is getting checked if there are some inconsistencies between the security descriptions, and if it is okay, it will be deployed on the real network and the network devices, and then we have the proactive monitoring area where this project is involved. So we want to monitor or verify if certain traffic applies to a specified policy. Therefore, we intended, because this is called lightweight, we have to use some small devices which have the capability of doing network. So we have used, or we're using PDAs and mobile phones as sensors, which collect the traffic and do the analysis, do some monitoring on that traffic. So the most important thing is to run a software, run an operating system on the small devices, which is capable of having a network stack and also to provide some capturing libraries. So we have chosen the family Linux distribution, which is a very small version of operating systems. It's coming from the Open Embedded initiative, and there is a currently stable version 8.2. It has the main features of this family Linux are that it has a packet management where you can easily retrieve additional packages for your system. It has also an X window system called TinyX. There are 2 different window managers called OP and GPE. The one is based on Qtopia, which is a fork of Qt, and the other one is based on GTK. So also many additional applications are available, but what we are needing is some kind of network traffic capturing and analyzation tool, and for the normal computers there exists is the Snort, and what we want to do is to use the Snort on these small devices. So how do we get Snort on the small devices? So that's the main competition. This was but very easy because we can use a tool called Scratchbox. With the Scratchbox, it's possible to cross-compile things you have in source code for Linux to run on very similar small devices. So the Scratchbox provides some tools where you can download your source code into the Scratchbox, compile it directly for your designated environment, especially for the ARM processor, which is used in the IPAC. And you can compile it on your host machine, which is much faster than compile it directly on the IPAC. So they are using a sandbox system, which is you don't interfere with your own libraries and dependencies. So to try to execute this, there are two ways. Either you execute it directly on the target with a remote sandbox shell using NFS for connecting to the target, or you're using EMU, which emulates the ARM processor. So as I said before, we're using Snort, and we're using Snort because it has a very nice modular architecture. So it is possible to write plugins for Snort very easily on different stages. So you can either write a preprocessor detection or output plugin. For our purpose, we have written a preprocessor plugin which analyzes the traffic and then gives an alert if there is something wrong. So what we want to do is network traffic classification. There are different kinds of network traffic classification. Either you can do it via using the packet header information, or you can do it also using the payload intrinsic features, like the character distribution of the payload. So the main idea in the positive framework was to verify and enforce traffic policies. So for instance, we have a policy only encrypted traffic is allowed in some special kind of network. So this policy must be enforced. Now you can either use your header information, like, okay, you know that on different ports are different protocols running. For instance, on port 22 normally is SSH, or you can look at the connection initiation if there is going on some handshake, key agreement, or whatever. But there are all problems. There are other problems, like you can use tunnels. So in these tunnels there is maybe in an encrypted tunnel there is unencrypted data, or vice versa. So we are directly basing our verification on the payload itself. So how we're doing this is that we are using the character distribution of the payload itself. So we are trying to analyze the payload, counting the characters in it and dividing it by the amount of characters. So we get a characteristic payload distribution for each packet, and maybe we can derive some parameters or features to detect, therefore, policy violation. So I show some example about HTTP and HTTPS traffic with the relative character distribution. The blue line is the HTTP traffic, which shows very much variance between the character distribution, and the red line is the encrypted traffic, which shows almost no variance in the character distribution. So this maybe is a good sign that you can use this character distribution to train some sort of network, a neural network or whatever, to distinguish between these traffic types. So we have chosen to use self-organizing maps, which were invented by Tybbe Kohonen and are some kind of grid of neural neurons, artificial neurons, and which have weights behind which resemble some input characteristics. So the most important thing is that you can map much as a high dimensional data to low dimensional maps. And this is also good for visualization to see what is going on in your network. The most important thing is unsupervised learning. This means you don't have to know anything about your network. The self-organizing maps will find the intrinsic features itself. So the most important thing is that there is a distance between feature vectors, which means each map, each unit in a self-organizing map has a parameter vector behind, which are the weights of this unit. And if you have an input, you also calculate some kind of parameter vector, and the distance between a parameter vector of the input and one of the map unit shows how good these two relate to each other. So we have the sum training. First we show input data. The blue one is the HTTPS and the red one is the HTTP. And there are some black points which resemble the sum units. So after the training, the map unfolds itself to the very interesting points of the data. The outcome is a distance vector matrix, which shows the relation between the map units and the distance between the map units. So, as said before, there are two types of training. First is to find the best matching unit, as called, to the input vector. So this means to find the best prototype vector or a parameter vector for the input in the map. So each unit in the map has a parameter vector, and you find the best matching vector for the input data in the self-organizing map. And then you try to rearrange the best matching unit to put it near the input vector. But also the surroundings and the neighbors of this unit, which matches best, are modified a bit. So this way the map itself organizes. So as said before, the best matching unit is the vector or the parameter, the unit in the self-organizing map, which is most closest to the input vector. So and the similarity between them is measured via distance. And this distance is used Euclidean distance. So how can we use now this self-organizing map to do classification? First, we are using the best matching units, and then we are using the input, the data, the test data, to find which we know. Okay, now we know the test data is either HTTP or HTTPS, and now we are using this the input data and find the best matching units in the for this input data, and counting the amount of hits for each unit. So we're finding the best matching units based on the hits for each input type. So on this slide you can see the hit-based classification for HTTP and HTTPS. The green points are HTTPS and the red points are HTTP. This is not a very big map, but we have been using smaller maps also, which works very well for the small devices. Only problematic is that some units match for both traffic. So there is a problem because if you try the input data, you can these units resemble both HTTP and HTTPS traffic. So there is an approach to use a more advanced a method to use sum trees where you use these matching units in the next step to train with this data again maps to separate this traffic. So how do we determine the hit rates for each map? Is now we collecting the, for instance, we have 3 units, and we counting the amount of how often this unit was hit by a specific kind of traffic, and then we get some the type of the unit. So, for instance, the first type was hit relatively 0.8 times by the HTTPS traffic, so it's clear that this one is a HTTPS unit. And we have also units which don't hit by known traffic, by unknown traffic. This is because we only want to distinguish between encrypted traffic and unencrypted traffic. We don't differentiate further between different protocols. So what is the problem is now is that it is often possible that more in a connection there are some packets misclassified. So to get a better result, we are using some kind of threshold of how much packets in a connection have to be from one kind of sum hits to classify it correctly as a type of traffic. So the training data set was collected using Snort. We used the Snort plugin to capture the traffic and separate it in different files for each kind of traffic. And we used this data in the training process and also in the determination of the sum hits for the protocol. So usually a training process would involve all of these 4 steps, but we are only using the first 2 because we have some kind of lightweight approach. Therefore, we don't using the kind of sum tree approach, which would be better for distinguishing between different protocols or more accurate. But as we will see, it is sufficient for differentiation between encrypted and unencrypted data to only use one sum map. This would be an example of a sum tree where you have the first sum has many 8 protocols, for instance, and can the first 2 or 3 and the second 4, 6, 9, and 10 are matching in same sums. So we are training a new sum and we're splitting them until we can separate them correctly. So how does the implemented system look like? It's, as I said before, it's payload inspection only. We are only using one self-organizing map instead of the sum tree, and using this hit-based classification. We have the implementation in Snort and MATLAB. The first, the traffic scanning and data preparation and data collection is a SNOM preprocessor plugin which captures the traffic and calculates the relative occurrence of the characters and puts them into the files. Then we have a MATLAB package for the sum creation and training, and for the output of the sum which will be used later in the detection sensor, which is also a Snort plugin and a preprocessor plugin. And this created sum is then used to compare the actual traffic with the sum. And this plugin reports all deviations from the normal or learned traffic. So this is a kind of scenario we are using in the positive framework. We have some wireless access point and some laptops accessing this access point, and we have the policy that only VLAN users are allowed to use cryptographically protected services, for instance HTTPS, SSH, or whatever. Therefore, we are collecting some kind of traffic which for training and doing this creating the SOM and creating the evaluation plugin for PDA. So we are able to verify if all the traffic in the system complies to the policy. On some, for instance, mobile users who are going around this area. So the results, as said before, the training was done with HTTP and HTTPS. We used about 4 megabyte traffic data for training. Only one SOM was used, and the hit classification was used for, with the trained SOM to classify the connections from the test set. So the results are very promising. We had a very good detection rate of HTTP traffic. We had almost only about 3 or 5% false negatives for this HTTP traffic. There are a small amount of packets only, but it's the same if you do it for larger packets amounts. There's similar. So the other thing is the connections which are using encrypted data. We have also a very low alert rate, except the one page with sms.at. And this is therefore because they are using some HTTP traffic outside the HTTPS. So they're fetching some images or whatever in this HTTPS traffic. But we are getting some false positives and also some false negatives. The most interesting fact is that although we have only trained this SOM for HTTPS traffic and HTTP, we were able to detect also with a very high rate that copy, the secure copy command does comply with the policy, and FTP and POP connections don't comply with the connections. So the conclusion is that it is possible, or very easy, to differentiate between encrypted and unencrypted payload, also on a very small device with very limited resources. And it is possible to better differentiate between more protocols if you use some trees, which has been shown in a paper by Udo Peyer, Peter Teufel, and Mario Lamberger. And the outlook is maybe we have to improve the accuracy and some problems with the payload size, because if you are using the relative occurrence, it is very problematic if you have a very low payload size. So there are some false errors. And we are completing the workflow for collecting, training, and classification in C, not to have to go to a MATLAB and to use creating a SOM, so that you can directly collect and create your classification plugin with Snort. And all of this will be available through the Positive project, which can be found at www.positive.org. Thank you for your attention.
Any questions for Stefan? All right, let's thank him once again. Remember to fill out your evaluation forms. Our next speaker is Christoph Bartz from the University of Bonn.
Yes, thank you, Ted, for the introduction. Yesterday, Peter Kaufmann has spoken about the Viola project. He has given an introduction and first results and status of the Viola project. And today, I want to focus more on special aspects of the project and the co-allocation of compute and network resources. And this is meant to be an integrated approach which goes from the application to the middleware and to the network. And the work on the co-allocation is mainly done by the Research Center Jülich and Fraunhofer Institute Sky, and the work on the network reservation system is done by University of Bonn and the Fraunhofer IMK Institute. So my agenda is as follows. I first want to give a motivation on why we want to do this, why this is important, and then I will go into details about how we can do this resource orchestration, as we call it. It's actually done by a concept that's called meta-scheduling. And after that, I will talk about the integration of the meta-scheduling service, or the cooperation of the meta-scheduling service with the network reservation system Argon. And after that, I will talk about some future works that we are planning to do in this context. So first, our focus is on those large scientific applications which might have extremely high data volumes and high computational demand. And what's also important is that they may use distributed resources, either in distributing the load to different clusters or using some kind of visualization environment or something like this. And an interesting point which I found lately in an article was the SPICE application, which is an application from America. I've found a test where this application was run on two different grids at the same time. It was the Terra grid and the UK NGS grid. And well, the lessons learned from these tests were that an automation in the process of co-scheduling is quite important for these applications. So we are doing this resource orchestration via advanced reservations. This is quite important that the local schedulers, which we coordinate, support this concept. And we are focusing on those computational resources, storage resources, also instruments, and also very important, the network resources. Some other communities that might benefit from such services are the astrophysics or climate research. Here the examples are of the DGRID initiative of Germany. So, and here are some applications that are taken from the Viola project. On the top left you can see AMG Opt, which is an optimal solver for special systems of linear equations. And this is more basic application. It can be used by several different kinds of simulations as a device, and this application there were run some tests with this application on several clusters. On the top right you can see the TechSim simulation. We have actually two different kinds of simulations in this part of the project, but this one is a simulation of silicon growth for silicon wafers. And we have three different kinds of physics here, and one can distribute those different simulations on different clusters. But there are also some license problems with those software, and so some parts of the calculation need to stay in one cluster, and other parts can be distributed to other clusters. On the bottom left you can see the Codavis application, and this is a collaborative visualization environment. It's concerned with atmospheric data, and an important aspect is that you can use heterogeneous visualization environments. On the one hand, we have in Jülich a cave where you can see this the climate data, and we can also have some different visualization clients, like 2D clients, and one can cooperate via a collaboration server and work on the same data sets on all these different sites. And on March, we had a demonstration of the project where we actually did some on-demand reservation of Ethernet over SDH for this application, and demonstrated that this application can run in the Viola context with those allocation of network resources. And on the top right, you can see the MetaTrace demonstration. And this is actually a project where we demonstrated the cooperation of resource allocation on different clusters and of the network. And I will go into details of this demonstration. So the problem this project addresses is the distribution of chemicals in the soil. And we can do a problem decomposition. On the one hand, we have a simulation that's called TRACE, and this is concerned with the calculation of the water flow, the groundwater flow. And on the other hand, we have this part trace simulation, and this is concerned with how the chemicals are transported in this water flow and what chemical reactions of the pollutants might occur. And we have to exchange some quite huge data amounts in the simulations, up to 1 gigabyte per second in this case. So we have from this problem space, the user can specify what cluster resources he or she want to use. So in this case, we've allocated the part trace demonstration on the Jülich Cray, and the trace simulations on the CESA, which is the CESA Institute, which is allocated at Bonn, and the other part of the trace simulation was run on another cluster in St. Augustine, which is near Bonn but not in Bonn. And you can also see the communication requirements from this application. Step means one step of the simulation, and data is exchanged 30 to 100 times every step. And on the other hand, the exchange of information to Jülich to this part trace simulation occurred more seldomly, but had much more data to exchange. And from this you can also derive the network requirements. We did a network reservation. We reserved multiple point-to-point tunnels and a layer 3 service on top of these tunnels. The tunnels ensured the traffic engineering and the quality of service. And I will come to this description of the network service later when I'm talking about the network reservation system. So I first want to go into details on how this orchestration process will work. And here's the example of the general Unicore architecture. It supports workflows, and a user can submit a job to the Unicore client, and the job is distributed to, or may be distributed to different sites, but what is missing is the co-allocation of clusters at different sites. The jobs are handled at the different sites via batch mode of the clusters, so one have to ensure that if you want to do co-allocation, that all these resources have to be allocated at the same time. And this is done by the metascheduler. And we also want to integrate the network reservation, so we need this network reservation system. And we also need some adapters the metascheduler uses to talk to this to the local scheduling systems. All local scheduling systems must support advanced reservation for this, and how this interacts, we'll see next. The first thing is that the user specifies the job, says on which clusters the jobs have to run, and the Unicore client, which has a special plugin which was developed for this meta-scheduling service, sends a request which is based on the Web Service Agreement Protocol to the meta-scheduler, and the meta-scheduler does some negotiation via the adapters with the local scheduling systems. How this negotiation is done, we'll see on the next slides. So if a common time slot is found, then this information is given to the Unicore client, and the job is submitted in the transferred to the Unicore system, and the actual computation of the jobs is then scheduled automatically. So the user has nothing to do with it anymore. It's done automatically by the system. These are the details of the meta-scheduling service, the meta-scheduling algorithm. You can see on the left side, it's a first fit search algorithm for common start time of all job components. The first thing this algorithm has to do is to initialize the requested resources and time constraints. So, and here you can see possible spaces of time in which the requests can start. This is determined by the resources on the one hand and the time constraints on the other hand. And now the algorithm really starts. We have also a startup time, and the availability of the resources is checked in parallel via available at service request message, which is a function of the requested resources on the one hand and the next possible startup time on the other hand. So we get results back from all the different resources, which are indicated by these arrows here. And if we have this information, the maximum of all those times is calculated as a candidate for a possible startup time. So, but as we didn't get a common slot for all those different resources, we have to do this iteration again. So this time, again, do the maximum computation. The resources, the availability of resources is calculated, and now we can see that we have a common time slot found, the maximum is calculated, and due to this calculation we can see that the next startup time doesn't have to change anymore, and so we found a common time slot for all those reservations. And in the next step, all those resources are allocated or reserved. Resources for this services are reserved on those different resources. So now I want to go more into detail of the interworking with the Argo network reservation system. As I said on one of the previous slides, we have a description of the network services that are going to be used. So you can see this on the right bottom side. A request can have a hierarchy of components. A request is composed of some request-specific part, which can contain AAA information, and several services. The services are composed of service-specific parameters, which might be start time, possible start times of the request, or latest end times of the requests, and also some connections that are involved in this service, and quality of service constraints for these connections, which can be bandwidth or delay. And on the top you can see a screenshot that was taken from the web interface of the Argon system, which shows a request that is composed of 3 different services, and on the right hand you can see the times at which these different services are requested. And the interface, which actually does realize the communication between the meta scheduler and the network reservation system, is shown on the left bottom. It has several commands. It's availability command, which is the command which I've shown you in the process of finding a common time slot. A reservation command, where the resources are actually reserved for the common time slot found. I will say some more words on the bind command on the later slide. The query is a command where the metascheduler can ask what's the status of the reservation, and in this case, what's the status of the network reservation. We have also a cancel command, which is where you can cancel some requests, and modification command, which might be quite important because it could be that a job lasts quite long, and you see during the lifetime of this job that the time you don't have reserved enough time on the resources, so maybe this whole computation will be lost, or you can reserve some more time if the network supports this. So this is a picture of the reservation lifetime. On the one hand, we have the negotiation phase, and the commands which are used in this phase are, on the one hand, the availability request, and on the other hand, the reservation command. And for both commands, we need to do an admission decision if we have enough resources available in the network, and we have to do this decision quite fast because, as you have seen, the metascheduler might check the availability of the network resource quite often in this case. So it's a question of performance. In the intermediate phase is the phase between the negotiation and the actual usage of the resource. We can do some re-optimization in this phase, schedule the network connections to different links, for example. And on the other hand, we expect the bind command from the metascheduler there. This is because the metascheduler doesn't know on which cluster resources the job will run at the time the negotiation happens. The local scheduling system decides just in time which CPUs will be allocated to the specific job. And therefore, we have to give the information on the ports where we can reach those different machines, or IP addresses the different machines have, to the network reservation system, so we can provision the service. And this bind command can arrive somewhere in the intermediate phase. It might also be included in the reservation, but should be there before the activation phase. If it's not there, the reservation isn't started. The devices aren't really configured because there's some information missing for the service. If the bind arrives earlier in this intermediate phase process, the activation is triggered automatically by the system. So we have these the activation phase, which, as I said, is the phase in which the network device is actually configured, and the duration of this phase may depend on the type of service which I'm going to use, or the type of interfaces which I have to the network components. It's quite different. Yeah, and the last phase is the actual usage phase. Here, re-optimization of the network connections might be very expensive because it might lead to an interruption of the service, so or some harmful influences on the service, so we are not focusing on this. But as I said, you could do some modification on the parameters. If you see that you need more network resources, the system can say, okay, I will give you these resources, or I will give you the resources for a longer time if you need them. But this is dependent on the network usage, if there are resources left for this. So these are different constraints which one might address. We have traffic engineering constraints and service availability, and these are the both constraints which we focus on right now. But one could also consider some policy rules or SLAs or other user requirements, and by this we get a three-dimensional solution space. And to do further network optimization, we can, on the one hand, in the negotiation phase, deliver more flexible kinds of reservations to the user. It's a first fit reservation here. This means you can delay the start point of the reservation to a later time. The user has to say that he's quite flexible in this, and the network system is allowed to do this. And on the other hand, for example, for file transfers or something like this, one can use malleable reservations. This means that either one is allowed to increase the capacity that is reserved for this network service and reduce duration, or reduce capacity and increase duration. This might depend on the capacity that's left for reservation on the different links for the service. And an optimization which may be done during the intermediate phases, rerouting of planned flows. As you can easily imagine, it's a continuous process. New requests for reservations will arrive continuously in the system, and at the point where the negotiation happens, we don't have a full picture on how what reservations will arrive during the intermediate phase of the reservation, and how the capacity that can be used for reservation will be in the usage phase. And so when more reservations arrive, we get a more complete picture, and we can do some optimization algorithms. For example, do some online algorithms that reroute flows, or have some offline algorithm like integer linear programming that can optimize this overlay structure we are building on the network. And this slide should address the problem which we get if we are considering multiple regions, multiple network regions. And on the top you can see the MPLS region, which I've shown you in the context of this metatrace simulation. And if there are not enough resources left on this layer, one could think of reserving more resources on lower layers. This could be done, for example, by a UniClient. In the Viola project, we have an implementation of the UniClient, a proxy UniClient, which can interface with the GMPLS components and do a reservation on the SDH part of the network. But if we use an interface like the UNI interface, it's quite hard to get some real traffic engineering on the MPLS layer, because we don't have any influence on how the connections are established on the GMPLS layer. In this case, we have used the UNI 1 release 2 version of the UNI interface, and this means that we have to establish the Ethernet service manually and provision the SDH connections via the UNI interface. But in this summer we will get a new release of this proxy client that will allow us
allow us to automatically provision the whole service Ethernet over SDH. So here's an overview on the concepts of the metascheduler. The metascheduler does resource orchestration. It negotiates with the different resources a common time frame where the reservation can begin, and it reserves capacity on different clusters and on the network. And the metascheduler also focuses on interoperability. We are active in certain standardization organizations and try to use common technologies. We integrated this concept into the Unicore middleware, and we used web services and web service agreements to do the negotiation. So, and on the other hand, the Argon reservation system comprises network resource management, which means we must do some resource modeling. We can do various kinds of optimizations on the network usage. We have this network service provisioning. This means we are automatically signaling the network components. We have end-to-end path computation, and we do service modeling. We also defined a policy-based framework for the Argon system and included the generic AAA server, which is developed in Amsterdam to give this AAA support. And we are focusing on different kinds of network architecture. We are focusing on multiple regions. As I said, for example, we are doing advanced reservation of network services in the GMPLS layer, like providing SDH connections, Ethernet over SDA services, and on the other hand, on the MPLS layer, virtual private networks on the MPLS layer. This is the status of the work which is done in the Argon system. We have developed a prototype implementation of the system and have demonstrated this special aspects of this prototype in March this year. And we are going to focus on multiple region networks, which means the interactions between the different network layers and different network technologies, and on multi-domain reservations in the last remaining year of the project. So this is how our future work looks like. Regarding the metascheduler, we want to incorporate some more automatic resource pre-selection. As I said, the user has to specify which resources he wants to use and how the different resources are distributed, and one could think of a more automatic process in this kind. And as I said, the Unicore environment also gives support for workflows, and this concept will be also integrated into the metascheduler, and it will be ported to Globus Toolkit 4, and also an integration into the IST Lucifer project is planned. On the Argon side, we are focusing on multiple region networks. As I said, the coordination of MPLS and the GMPLS layer. We want to do some enhancements on the resource and service models of the prototype, and are planning a cooperation with Jiangdu and integration with the interdomain manager of GRR3 and also Lucifer integration. So I come to the conclusion. We have incorporated an integrated approach and an application-driven resource selection, which is based on Unicore. We've shown a co-scheduling concept. We've I've shown you how the different resources are allocated, including the network resources. This is done by a meta-scheduling service, which does actually the orchestration of the resources. And Argon provides an advanced reservation mechanism for network services with a dedicated CROS. Thank you. You can see some further information on the Viola testbed network site, or can also write emails.
Do we have questions for Christoph?
Thank you. You're supporting GMPLS ASON on the diagram there. How are you guaranteeing your reservation in that scenario? Is it only your application managing the network, so you know what your overall bandwidth is, or can you handle situations where you can determine that a request will succeed at a point later in time?
Yeah, this could be done by a network manager, which keeps track on the status of links, so you can, for example, schedule some maintenance functionality where links will get down in the future, and this network manager can also detect failures in the network, so the reservations can be rerouted. Did I get the point of your question? Or?
So when you go to do a reservation in the future, how are you determining how much bandwidth is available at that time and if you can satisfy the request?
Yeah, we keep track of the link usages of the GMPLS layer then.
Okay, so you're actually listening to the routing. You're when signaling occurs, or sorry, when you do the reservation, you're pre-computing the paths to determine how much bandwidth is available?
Yeah,
okay.
That's true.
That's fine.
Anyone else? All right, let's thank you once again. Yeah, we're doing a little switch here because our next speaker, Bram Peters from SurfNet, is going to do a demonstration.
Well, I hope it's going to work, but laptops, networks. That's at least a screen. So, my name is Bram Peters. I work for SurfNet in the Network Services Department, and one of the things I do is managing our Lightpath network and making sure that the dynamic services that we want to provide in that will eventually be deployed in a nice and easy to operate way. So that's why I've gone for a title that's 2 lines long. I'll give a quick introduction, then I'll talk about what the Lightpath service that I'm looking for will look like. I'll give you one slide on the problems, give you one slide on what the architecture basically looks like, interacting with the service, managing the service. That's where I hope to be able to do a demo if my VPN client hasn't died. And then one slide on the open issues. That should give me 8 slides, but actually there's a bit more. So, SurfNet 6 is a hybrid network. So we have built a network on our own dark fiber infrastructure. Our main thing that we do still is IP routing. So I'm not going to get into the discussion about packets versus circuits. We still do IP routing. That's core business. But on the other hand, with this network, we can also provide direct layer 1 point-to-point connections. That is a new service. That is something the new network has delivered us, and we see quite some uptake of that. However, dynamic light paths as dynamic, we don't do them yet. That is one of the target innovative services that are part of the big plan, and we plan to actually provide that within this year. Doing that, because I also operate the network, or I'm responsible for making sure that all operations flow smoothly, I want to be able to do that in a manageable way. So what is the service we're looking for? Light paths are basically, as said, point-to-point layer 1 connections, at least that's how we provide them. They look like a virtual lambda, as in if it were a lambda, you wouldn't know the difference. We cut up 10 gig links into subparts, but that ends up at the same port, and you don't see any difference in jitter or delay. The edge port that we have now is mostly gigabit Ethernet, but we expect to be able to provide 10 gig for this service as well. And subrate is possible, so it's not because you have a 1 gig edge port that you do need a 1 gig service. It's, for example, you could request 155 meg, 200 megs, 751 megs, and we will provision something that comes close to that. Actually, is a bit more when necessary, but you will get your 751 megs. Why do we want to do that? Basically, point-to-point light paths are good because they will divert your high bandwidth streams from the routed core, which is useful for storage and quite a few other applications in the more mundane worlds. But they also allow you to create optical private networks, which is where we have seen quite some uptake. That's basically where institutions build their own network over our network, connecting their routers to each other, and then at one point in the network they will get an IP connection. And then as a third, another minor point, light paths are actually quite interesting as an integral part of scientific instruments. I will refer to, for example, the telescopes that we have the hub for in Dwingeloo, which is carrying quite a lot of bandwidth. We are expecting to provision about 20 gig to that site. And obviously, because they want to be able to connect to different telescopes, or different people may want to connect to the hub sites, at some point we will want to have these as dynamic as possible, or it should be possible to have them dynamic. The dynamic service, therefore, is scheduled user provisioning. We do not interfere with that. We allow a user to control our network through an interface that we trust, and we do that on a managed network. So you do get a flexible, reliable, guaranteed, controlled, and managed service. I have been adding words to this during the week, depending on the comments I got from people, but that is what we're looking for. However, we do see problems. Basically, the first one is, how do you get a schedulable, guaranteed on-demand service? How do you get secure, simple user access? As in, we do expect scientists to use this, not network nerds. I'm one. I don't expect everyone to be one. Then, how do you share production network? Because we have quite a large network, but to be able to provide this service, you need to have extra bandwidth. And at the same time, you want to make sure that a system that does on-demand provisioning isn't going to impact your planned provisioning on the network. Will stick to the bandwidth you allocate to it. So you have to be able to allocate ports to it. And on the backbones, you have to be able to allocate specific time slots or a specific capacity to it, without it actually having been provisioned already. Fourth bullet point, we want to be able to control user access and have policy management. Basically, it's not because you open a port up to the public that everybody is the public. You want organizations to be able to tell, these are my users, they can access my ports, and I'll have these users from other institutions connect to my ports, but we want to be able to control that. On the other hand, we don't want to get involved in adding every individual user to the network. So at some point, we want to delegate the management of end users to local group managers who are in institutions who have been asking us for ports that are controllable by DRAC. So at the same time, the initial policy that we're looking for has to be open enough to simulate initial uptake. I've had quite a lot of discussions with our directors on what that should be like, and we think that the initial model is going to be simply, you have a port, everybody can connect to it. Therefore, everybody who buys a direct port will eventually be able to connect to each other. But I'm quite sure that at some point in time, people will definitely go for the closed model, where you have your little own network with your own ports, and nobody can come to them except for the people who are in your group. Once you have that kind of discussion, you end up with many different models of what's possible, and we want to be able to provision as much as that in a flexible way. So policy management is quite important to us. Then you need to do accounting as well, so you need to keep track of all services that you've been provisioning, because at some point you want to tell people you've been using this much, maybe you should buy another port, or you basically want to know how much you need to provision in the network to be able to support most of the services, because this will be blocking. We do dedicate bandwidth to it. Once you've reserved something, we have dedicated the bandwidth for you. So because the network isn't infinitely large, there may be some blocking at some point, and we want to be able to avoid that as much as possible. Another one that we had quite a lot of discussions on are alarms. Since the beginning of this week, it's called knock noise. That's basically when you have an automated system provision something on the network, you will see the alarms of the provisioning. Now, we've got a knock who are looking at the network 24 hours on 24 hours, and they see all these red lights flashing on nodes that are part of the normal network. Should they act on them? They're alarms, so in principle they should. Whereas if you have a service like this where people come and provision connections on demand, the whole network may be flashing the whole time, which isn't nice. So we want to avoid that as much as possible. There are ways to do that. We're looking at what the best way is. And then the last point is interdomain. We've had lots of interesting discussions on that, but I still don't know how to do it. So it'll end up at the issues slide at the end. So the basic architecture for Direct, basically, at the bottom we have the actual network nodes. There is an OME and an AGXC, both are Nortel products, because basically we have both a Nortel network. And I'll start from the bottom because I like to start from the bottom, and I understand that. The bottom block in what is Direct, that's the 3 gray blocks, is the Direct Nodal Resource Manager. I should say that Direct is a product we developed together with Nortel. We provide lots of feedback, and they change it depending on what my wishes are. It's true. If I want an extra button, I get one. The bottom block is called the Direct Nodal Resource Manager. That's basically something that is doing the network element abstraction. That is looking to be able to incorporate any other node later in the system, be it a layer 2 node, a layer 1 node, be it a Cisco node, be it an Alcatel node. In principle, Direct should be able to control any node that is a node where you can schedule a circuit on. Once you have that element abstraction, you can add the node to the light path control plane, that is dynamic management of resources. And it is server-based, which allows us to basically manage nodes that are not control plane enabled, and we do not need to put an extra switch or anything else next to it. We basically have element abstraction at the server, and we do all the computing at the server. That control plane does the provisioning, does the basic day-to-day mechanical work of what it is good at. But that's not going to provide you schedules. So that's why we have a Direct Network Resource Broker on top of that does bandwidth management across the planes and provides you all the routing intelligence you want. So we are thinking about adding more routing algorithms, and once it's up and running, we can think about optimization as well. That's the block. That's called Direct. Then we have a few interfaces. There are 2 user interfaces. We call them UNI or USI, the user to network interface or the user to service interface. One of them is a web GUI that I hope to be able to demonstrate to you in about 2 or 3 minutes. The other one is a web service interface. So that allows any application to interact with the service as if it were a user, and you're going to get exactly the same functions. The second interface is the Direct administration interface, because obviously we are only telling people what nodes at the edge they can connect to, but there's quite a lot to manage inside the network. We have to dedicate bandwidth, we have to allocate ports to specific users, we've got to create the groups. And then the last interface towards the outside world is the AAA. We've gone for an external solution, in this case A-Select, which is not really external because it's a SurfNet thing. And that allows us to do authentication of users outside our domain. So we can hand over the management of end users to people who are at the edge. So what does it look like in practice? A nice graph that hopefully works. So the first thing you do is you have DREC in the network that has a control plane sitting at the bottom. Through the administration interface, you tell the system what the control plane is allowed to talk to. So that's building up relationships, finds the topology, and does it all in an automated fashion because that is what control planes are good at. Secondly, you have an interface from the user towards DREC that isn't the public domain. It's simply you go in a web browser, you type your IP address of the server, and then you can schedule whatever you want to schedule or what you're allowed to schedule. Once your request is coming up for being provisioned, DREC goes about its business, talks to the nodes, provisions the connection for you, and to you it looks as if you have your point-to-point light path. So you will not see that it's actually going through the white dashed line. It's going to look as if it's a point-to-point connection. So what are the interactions you get as a user? I've been dividing them into 3 different functionalities. Basically, the first one is you can query for the feasibility of something. So you can browse the system for, would I be able to do this? It's going to tell you what ports you can get access to. And then it's also going to tell you, will I be able to get a service from that point in time to that point in time with that bandwidth? It's not going to give you a guarantee on that, because then you first need to click the button that says, yeah, I really want that. But that allows you to do some potential interfacing, and I think that's probably going to be quite useful in inter-domain scenarios where you want to know what a system may deliver you, but allows you to crank back on your reservation as well. So obviously the second thing you want to do is really schedule a service. You query the system, it tells you at what costs or other parameters that you've specified you will get the service, and then you click the button that says reserve. You get a confirmation, a reference number, and a guarantee of the parameters. So you are sure that at that point in time you will get that service, unless the whole network breaks down, but then that's like a normal incident. You've now made your reservation. Obviously, at the moment in time where the reservation comes true, the service will be established, and you can verify what you get. So you'll get you're able to verify the state of a reservation. Have I actually reserved it? What were the parameters again? Am I still happy? Do I need to delete this? Once the connection is up, you get a status request that tells you, yeah, it's up, or then it's broken. So that allows you to do something else in case you need to do something else, and you haven't ordered the protected version, for example. And then to do that, the initial way of doing that would be a trap. That's an email, or you go on the website and you click to verify. So that's the point where I wanted to demonstrate the end-user GUI. I now hope that my VPN hasn't died. It hasn't, apparently. So this is the user interface. The IP address is one of the servers that we run in Amsterdam, so this is the real test bed. And I'm simply going to show you how it would be if you were scheduling a connection. I'm probably going to have to log in again. Yep. I can type faster than I think. Okay, so that's where you get the list of endpoints you can get access to. So basically we have 3 nodes in our test bed, and if you can read the small print, it says node 3 port 1, node 3 port 2, node 1 port 1. All of them are out of service at the moment because they're not connected to anything, but in a managed environment that would be an incident, so someone would be solving the incident in the NOC. This gives you a list of the ports you may get access to at some point. We've logged in with a DREC account, so it shows you all the DREC enabled ports, or basically it shows you all the ports that are dedicated to the DREC group. So that's purely informational. What do you do if you want to schedule something? You go to the create schedule. So you give it a name for your reference. You give it a rate that you want your connection to run at, for example, 670 megs. You tell it what port it needs to get to. or you tell it what port it needs to get from and to, and then I'll check what I prepared. That's node 13244. Because I've got a few connections running on the system already, so I want to make sure that it's going to not fail. Sorry. So I'm going to run that in about 3 minutes. So that's from 5:20 until 6 p.m. And I'm not going to have a recurring schedule. I'm just going to create this one. Destination TNA cannot be empty. Okay. Now hopefully this is going to work. It's been very reliable all day. Squeak.
Yeah, node 143 was a port, node 341.
13244. So that's what you get. It's been working all day nicely, and now it doesn't want to do anything. In case it really doesn't work, I've pre-scheduled a few things. So there we go. Okay, so
I pressed the button 6, 7 times and eventually works.
so it says schedule has been created successfully. So you do get a guarantee now that you will get exactly this schedule. As said, I've been trying to be cautious, and I pre-scheduled a few things. We can now look at the list of the schedules that we've created today and what the state of them is. For example, this is the one we just created. You get the information from when to when, from what port to what port, the rates, and what the state of the reservation is. And at this moment, it's pending. So this means we are planning to actually provision this stay with us until it's 5:20 on the server, which should be in about a minute. So that's the user interface. That should be fairly easy to understand. We're redesigning the GUI. I've asked for more buttons. I've asked for more options to be included, but it's still the test system. So back to the presentation. So I didn't need the GUI snapshot. Good. How do we turn this into a real manageable service? So basically, I've been talking about a service user who should not know anything about the system. He simply goes to his group and says, I want to register, I want to use DRAC. So he gets locally registered with the group, then he gets a credential added to the local server. He logs on to DRAC through a website. He then schedules services, he uses the services, he verifies the service. So that's easy. On the other hand, it's us, SurfNet side. We have to add network resources to DRAC. We have to create the groups. We have to assign ports and resources and policy to the group. And as a last thing, we also allocate a group manager to the group, or a few group managers. They're on the user side, and they will add users, as in real end users, to their group. They can manage selected user rights, maybe only allow someone to get to 2 specific ports. They will also get the accounting of their service based on their group. And if that accounting shows that they're running out of bandwidth, they need to ask us to provision more ports. So that's all nice. That's the direct service. But obviously, this is still running on a managed network. So we have network operators sitting in our NOC watching the screens the whole day. They need to know about the service. They need to know that this exists. They need to still manage network incidents. If a port is out of service, because nothing is connected to it or because someone cut the fiber, they need to act on that. They do not need to provision on direct resources, so we need to maintain administration on what is allocated to direct and what is allocated to the other production network, because this is a production service, so they shouldn't be running over that production service. I've been talking about administrating, so basically there is an admin GUI as well. Initial function is to assign nodes, ports, and backbone bandwidth to DRAC. DRAC will only get access to selected parts of the network. I want to make sure that DRAC, which is a dynamic autonomous tool, doesn't go and creates connections on places where I don't want it to do that. So there needs to be a clear separation from these static production services, and I need to be able to add that specifically to the node. At the same moment, because we have limited bandwidth in the backbone, we will at some points share 10 gigs, so we need to be able to divide the 10 gig into direct part, non-direct part. Then There's the access management. So I've been talking about the creation of user groups, assigning the group managers to them, adding policy, which is you tell what port belongs to what user group. And again, in italic, end users are added to groups by group managers. So I hope that it's going to be a very successful service. Therefore, thousands of people will want to get access, and I don't want to have to type thousands of users into the system. Third function in the admin client is connection control. So basically, we want to be able to still manage and control the individual connections in case things go wrong, in case we want things to be rerouted on other networks to be able to do service or maintenance on the network. We want to be able to cancel connections when people have made a mistake and they're feeling very unhappy about it. And the fourth function is monitoring. So we need to have state of the DRAC control network that will only look at the DRAC controlled service. So we filter the state. If a B feed on a node goes down, that does not matter to DRAC. That matters to the people at the NOC. It is not a replacement of the management system. I still want people who manage the network to not have to deal with this as a service. And on the other hand, I don't want to have people who manage the DRAC service to need to care about standard service incidents. There is also planning view where you can get the usage of a link, the usage of a port that allows you to plan for upgrades, see where the network is actually being heavily used or where it's not heavily used. And then the last thing is accounting. So we keep track of all connections that have been provisioned, what groups they are provisioned for, and then we can hand that to the group managers and eventually perhaps bill them for it, which we're not planning to do initially because we first want uptake and then we think about billing. So again, the admin GUI, I hope that it's still working. This is what the admin GUI looks like. So basically this is our testbed, 3 nodes. What the orange line you see now is a schedule that is currently running. I'll do retrieve of the schedule. So this is the list of all the schedules that have been provisioned on the network since the last server reboot. There are still things we need to work on. I think it's actually a whole new load we put on, and it forgot about all the previous things. So we see 2 calls in progress. That's the one we just did. No, that's one I provisioned before we came in. That's one that's going through 2 nodes for the simple reason that in the facilities management, which is where you add resources to DRAC, I have been careful to not set the ports on that upper link to be assigned to DRAC. So I will filter on the STM64 ports. So these are 10 gig links between the nodes. And if you look well, we have 6 10 gig links, or actually there's one going to a different node. I've made 4 of them INNI, and 2 of them are still OSS, so these are still controlled by the standard network management system. DRAC does not know about them when it's doing routing. So that's why if you provision a connection between the node on the left and the node on the right, it's still not going to find the shortest route in the network. It's going to go through the bottom node. Going back to the scheduling. So I've got 2 in progress, but I thought I would have 3 in progress. So I allow myself to do a quick check here of the status. Need to log in again. Okay, John, you take care of that. So I said it's been running nice the whole day, and now I get these. Yeah. Submit. So John who's talking to me now is actually the guy who does all the adding buttons to it and makes sure that I get my buttons. So it's still pending. Not happy. Oh, it's not 5:30 yet, so actually that's okay. It's on the server, it's 5:26. I put this to be at 5:30. I should have been a bit more careful. So I'm still happy. I think that's basically what I wanted to show about the admin client, that you can basically add specific facilities to direct control, that you can look at a list of schedules. It allows you to do basically all the network administration you need to do to be able to run such a service. So back to the actual talk. So I hope that did give a good feeling for what DREC is doing and how we think about operating that. We still have a few open issues though. One of them is reducing all knock noise. We've been thinking about what knock noises are easy to take out, but it is quite difficult to really make the alarm profiles such that you're never going to get any alarm that's simply related to the provisioning of direct services and not squash alarms that are related to the actual service. So when someone breaks a real running direct service, I still want the knock to act on it. I don't want them to act on alarms that are just part of the provisioning. Then there is a big issue of interdomain. DREC has a very good domain functionalities. So on the domain, we can basically do whatever we want. We have edge ports that you can provision connections between. It does that on a scheduled basis. So that is a nice shell from the actual network. We allow ENNI ports and UniPorts to be managed in a different way because we have them different in the system, and we have interfacing flexibility through web services. At the same moment, there is a great potential for interdomain functionalities. DREC can learn topologies from other domains, but it's a lot more difficult what you would do about policy. We've been thinking about a few policy models. Other people may have other policy models. How do you communicate these? So, in my view, there is some need of standardization, but I'm not sure where and how much you actually need to standardize. It's not obvious at what layer you need to standardize, because DREC is a service. It's not a control plane. The control plane is running beneath it. But I want to present it as an interdomain service because I want to be able to do scheduling across domains. I want the richness of it. And then there is the last point about the campus domain. We've got, once again, something that works nicely on our SurfNet domain. But to extend the service to the real end user, you still need to do something on the campus domain. It's not good enough to bring something to the edge of the campus and then have the end user sitting at his desktop still not getting the connectivity he wants. So DREC may control layer 2 VPNs at some point. It's actually in the planning, but it's not going to be in our initial release. So that's about within time, I hope.
Any questions for Bram? Yes, right.
So I can still demonstrate a bit more.
Well, just a question. I mean, when you say that you can learn topologies from other domains, what do you exactly mean with that?
Well, basically, DREC can take in a topology, it can take in a node, it can take in information about endpoints, and then integrate that as if it is a abstracted node as well. You've seen the blog that does nodal resource management. You can use that to talk to other domains as well.
We understand other direct domains?
Well, that's where you do need the standardization on how you want to do that. I think there are ways of doing that. We've got a way to talk about the nodes, and that's where you do need some agreement on what it is you talk about. It's in my issues list.
Okay. Thanks.
We did do a demo earlier in the year where we integrated
We're not casting, so you got to make sure.
Oh, okay. We're talking about
Yes, a couple of quick questions. When you were describing in one of your slides the service users, group manager, service manager, all this flow that needs to be done in order to provide the service, do you have specific SLAs with your users? And have you defined what is the lead times for delivering these services? And the other question is, currently, how often do you have these requests and for how long?
So, as you have seen, I've done the demo on our test bed. We're not actually running this in our actual network at the moment. The initial service we are going to provide is not going to be a SLA'd service. It's going to be use it, try it, tell us what's good with it, tell us what's wrong about it. And it basically comes down to providing a PERD at the edge of our network, assigning that PERD to direct control and having bandwidth in the network that is direct controlled. I can do that in 5 minutes. That's not going to be according to our NOC procedures, but the actual provisioning of the service is quite fast. I think you're going to spend more time getting people to have their patch cord connected to our PERD than it takes time to actually do the management within DRAC. And obviously, once you are connected, you can use a service, assuming other people have PERDs as well that you can connect to.
Any other questions? Okay, let's thank Brian once again.
Flight to
Oh, this is the one, yes.
Did I think I told you?
Yeah.
Where do we stick this in?
And round the back. Can't it be like Max and have it something sensible inside? Yes, I suppose Etna's a bit of a letdown, really, isn't it?
That's hidden behind haze, and one very enthusiastic person was telling me, no, that's not haze, that is eruption. The city doesn't generate haze, it's all from Etna.
Oh.
Just scroll down.
Oh. So if I just whack that folder across. Eject it properly. Wow. That's amazing. That would liven them up. So you're going back to... Oh, you're off to see your twin brother or something, aren't you?
That's right, right.
Are you all your family spread around the world?
Well, I haven't got such a big gang. They're in the UK. And then this twin brother has been around, he married around less.
Right.
Yeah, and they lived for a short while in London. She was unhappy.
So you originally...
South Africa, Turkey.
Oh, okay. But you've just all decided to go to different places. So you don't get to see each other very often then?
Well, I'm registered with them, so they do come out to babysitting gigs.
Oh, that's good. Oh, gosh. Now? Do you want to start now? Well, that's it. I think it might be worth starting, but you're just going to have to go into face up to the fact that some are going to be wandering in, aren't they?
Oh, indeed. But I think that anybody who wants to.
And it's an easy room to get into, this one, without disrupting. Okay, we'll make a start.
I mean, a lot of people here just wear email.
Okay. Good morning, ladies and gentlemen. Congratulations for getting up so early this morning. I'm impressed. I hope you haven't got sore heads, but hopefully you enjoyed last night's evening meal at the very splendid palace with all those wonderful painted walls and ceilings. Anyway, this morning's session is on research networking beyond Europe, and we've got 3 very interesting speakers covering most parts of the globe. Our first speaker is Michael Stanton. We have some technical problems.
I don't know how to put it on full screen. It seems that the reader is not reacting.
I'll carry on introducing Michael whilst we get the technology working. Michael was born in England and completed his PhD in maths at Cambridge University, and since then he's been working in Brazil. And he's Professor of Computer Networking, so I'm surprised he can't operate the technology.
It's not a network.
Anyway, he's going to talk about Red Clara and integrating Latin America into global R&E networking. Michael.
Fine, thank you, Shirley. Good morning, everybody. I managed to pick the short straw and be the first person to talk after last night's gala evening, so welcome to the people who are here on time. I'd like to thank very much the invitation from Terena to be here. The work I'm going to talk about has involved a lot of people over the last 4 years or more, including notably my co-author here, Catherine Sturver from Dante, who is the project manager for the ALICE project, which I'm going to talk about here. I have a rather dense agenda. At the last slides refers you to the paper, which is also on the website. It's not quite properly formatted, but it's got all the information in, and rather more than I'm able to present here. I'd like to regard both the paper and the transparencies as a kind of reference material, and so I don't intend to sort of go through it very slowly because there isn't the time, and I hope that some of the information might be useful for reference later on. The structure of the presentation is as shown here. I want to talk a bit about the origins of, about what is Red Clara and about then the origins of academic networking in Latin America. Latin America hasn't interacted much in the past with Europe, but this has improved in recent times. But it's interesting to see how old this practice has been and its ups and downs. And then there's talk about the ALICE project and the creation of Red Clara, which is the subject of the main subject here.
Then recently formed national research and education networks in Latin America, which is a rather exciting outgrowth of the ALICE project. Something about new networking technologies. This is mainly optical technologies which have been used, which are being used in some of the NRENs in Latin America, and we're quite pleased with how we're working in this area. And then to finalize, to talk about the benefits of this new networking infrastructure for cooperation between Europe and Latin America in research and education. So I'll start off with introduction to Red Clara. This is a new regional network in Latin America. This interconnects 14 of the 18 targeted countries of the ATLAS program of the European Commission, of the Directorate of Europe Aid, and it has been built with through the ALICE project, which is coordinated by Dante, and in which participate 4 European